Lollipops, muffins, and chocolate chip cookies are crafted through a precise blend of heat timing and irresistible ingredients. We dive into molten sugar, pulled into glossy spirals, fluffy batter portioned with machine-cut accuracy, and dough studded with rich chocolate pieces as industrial lines transform simple mixtures into iconic treats. Today, we follow each step from raw components to packaged perfection, revealing the surprising science and meticulous choreography behind these classic sweets. Lollipop production begins with dry granulated sugar and glucose syrup, delivered in bulk into silos and heated stainless steel storage tanks. The sugar is conveyed through screw feeders into a large dissolving vessel. Simultaneously, glucose syrup is pumped through jacketed pipelines to the same vessel. Water is introduced at a controlled rate to create the initial slurry. The temperature is raised to approximately 110 degrees, while agitators rotate to dissolve all solids. The mixture becomes a clear, homogeneous sugar solution. Once the sugar is fully dissolved, the syrup is transferred via gravity or pump into a vacuum batch cooker or a continuous candy cooker. The cooker raises the syrup's temperature to 145 degrees to 150 degrees, while lowering the internal pressure. The reduced pressure allows water to boil off rapidly without degrading the sugars. The syrup thickens into a dense, high brix mass. Sensors monitor real-time concentration and adjust heat and vacuum accordingly to maintain the target range, typically 98-99% solids. The cooked candy mass exits the vacuum chamber through a heated outlet, either dropping onto a stainless steel cooling table or into a rotary kneading kettle. On the cooling table, scraper arms fold the mass over itself as it cools. Inside the kettle, mixing paddles rotate at set intervals. The temperature drops gradually to about 90 degree cooks. At this stage, flavor oils, acids, colorants, and emulsifiers are added. Dosing pumps inject precise volumes of ingredients based on the batch weight. Mixing paddles distribute the additives evenly throughout the mass while avoiding air entrapment. If a layered or dual-color lollipop is being produced, the candy batch is divided into separate portions. Each portion is flavored and colored independently in separate kettles. A heating jacket maintains each portion at a stable working temperature. When ready, the portions are loaded into a batch former that can extrude them side by side or swirl them together during the rope formation process. Once mixing is complete, the candy is transferred to a rope sizer. The mass is fed into the machine and drawn through a series of sizing rollers that reduce and elongate the bulk mass into a continuous rope of uniform diameter. Each roller pair incrementally reduces the thickness while maintaining roundness. Servo-driven rollers and load cells ensure tension remains steady along the entire length. Inline cameras monitor the rope diameter within plus 0.5 mm tolerance. As the rope advances, it enters the forming section. Here, it is pulled into a rotary die forming machine. This system consists of two steel rollers with precision-cut cavities. As the rope enters the nip point, a stick is inserted from below by a mechanical arm into the soft mass at the exact moment of compression. The die cavities close, shearing the candy rope and forming the lollipop head around the stick simultaneously. Sticks are fed from a vertical hopper onto a horizontal conveyor where they are spaced using star wheels. They travel into the insertion mechanism where grippers or push rods insert them directly into the hot candy as it is formed. The insertion depth, pressure, and angle are all adjustable. Any stick not aligned properly is automatically rejected before contact with the product. After forming, lollipops drop onto a cooling conveyor. The system is divided into zones with progressively lower air temperatures, beginning at around 25 degrees Celsius and dropping to 10 degrees C. Air is circulated through HEPA filters to remove particulates and maintain constant humidity. Cooling takes 5 to 8 minutes, depending on candy size and formulation. The sticks are kept horizontal to prevent gravitational deformation of the still soft candy head. Once fully cooled and hardened, the lollipops enter the wrapping stage. Multiple high-speed wrapping machines operate in parallel. Each machine feeds film from a large roll. Photocells track registration marks to ensure proper logo alignment. Film is cut into pre-sized sheets and fed into the wrapping jaws. Lollipops arrive single file via guide rails and timing screws. As each piece enters the wrapping section, it is met with a film sheet. The candy is centered on the wrapper, and the machine either twist wraps the film at both ends or folds it around the head and seals it with heated jaws and pressure rollers, depending on the wrap style. Speeds reach up to 800 lollipops per minute per machine. Sensors verify the presence of each stick and confirm film seal integrity. If a lollipop is missing a stick, misaligned, or improperly sealed, it is rejected via an air blast or servo diverter. Properly wrapped lollipops are conveyed to a grouping area where they are accumulated for final packaging. Packaging varies depending on format. Some lollipops are bagged in high-speed, vertical form-fill seal machines. The wrapped candies drop into vibratory feeders that portion them into buckets. Buckets empty into a forming tube where plastic film is formed into a bag, filled, and sealed on the top and bottom. Sealing jaws cut and compress the film simultaneously, producing a finished pouch. For tray packs, lollipops are grouped into clusters using a belt divider. Robotic arms or pushers load fixed quantities into cardboard trays or blister packs. Cartoning machines erect the trays, insert the product, and apply hot melt adhesive to seal the cartons shut. Inkjet or laser printers mark each pack with batch codes and expiration dates. Cartons flow to a case packer, where they are grouped and packed into master cartons. Mechanical arms fold the outer box and glue or tape the flaps. These boxes are stacked in layers on pallets by robotic palletizers. The system alternates stack orientation by layer for load stability. Slip sheets are inserted between layers by a vacuum picker. When the pallet is complete, it transfers to a stretch wrapper. A rotating arm or turntable applies a pre-stretched plastic film around the pallet. Wrapping parameters are adjusted based on pallet height, product weight, and load configuration. Once wrapped, each pallet receives a barcode label and is conveyed to the shipping dock. All stages of lollipop production are managed by programmable logic controllers. Every machine, cookers, rope sizers, forming presses, stick inserters, wrappers, and palletizers is integrated into a plant-wide SCADA system. Operators monitor real-time metrics, including syrup concentration, rope tension, cutter timing, seal temperature, stick depth, wrapping accuracy, packaging speed, and output count. Cooking systems are equipped with conductivity probes and pressure sensors. These devices ensure consistent cooking profiles by regulating steam pressure, vacuum levels, and temperature. Flow meters control syrup and water ratios during dissolving. In the cooling tunnel, temperature and humidity sensors maintain conditions within tight limits to avoid surface cracks or bloom on the hardened candy. Line synchronization is maintained through encoder feedback. Rope feed rate, die rotation, and stick timing are adjusted in real time to prevent drift or misalignment. High-speed cameras inspect each lollipop post-forming for symmetry, stick centering, and surface quality. A quality control logic system tracks defect rates and triggers maintenance if thresholds are exceeded. For striped lollipops, colored candy masses are co-extruded through a color stacking head before entering the rope sizer. Stripes are achieved by arranging differently colored masses side by side or spiraling them with twist control. Layer geometry is controlled by adjusting feed angles and rotation during rope pulling. Dual flavor or filled lollipops use concentric forming. An inner core, often a soft center or powdered flavor pocket, is co-deposited during the forming process. Dual extruders feed the core and shell simultaneously through concentric nozzles. The rope is cut and shaped with the filling encased completely inside. Production speed depends on format. A single forming line can produce over 1,000 lollipops per minute. With multiple lines operating simultaneously, output scales into the millions per day. Each system runs continuously with minimal downtime. Quick release tooling and automated cleaning reduce changeover time between flavors or shapes. Cleaning in place systems are installed on all cooking, mixing, and delivery equipment. These cycles run automatically between batches. Hot water flushes remove residual candy. Caustic detergent circulates through tanks, pumps, and piping. A final rinse ensures all surfaces are food safe. The cleaning process is monitored by conductivity sensors and logged by the control system. Sticks are produced off-site to specification and delivered in bulk. Materials range from extruded polystyrene to compressed paper. Before entering the line, sticks pass through a stick inspector with vision sensors to check for length, roundness, and cleanliness. Only compliant sticks are fed into the press. Any deviation beyond plus 0.5 mm in length or 1 gralus of bend results in rejection. Muffin production in a factory begins with the precision handling of core ingredients: wheat flour, granulated sugar, vegetable oil, eggs or egg replacer, milk or whey solids, water, leavening agents, salt, emulsifiers, and flavor additives. All dry materials arrive in super sacks or silo-fed bulk containers. Liquids are delivered in food-grade tankers and pumped directly into insulated holding tanks. Ingredient feeding systems are automated with load cell-equipped silos, volumetric dosing hoppers, and inline mass flow meters that measure and control exact quantities in real time. The mixing process starts in a large-scale planetary or horizontal mixer. Flour is fed from silos through enclosed pneumatic lines. Sugar is metered in by screw feeders. Liquid components, including water, oils, eggs, and emulsifiers, are introduced from jacketed tanks through pressurized dosing pumps. The mixer uses high-torque arms or paddles to fold the batter, and a PLC-based control system sequences ingredient additions based on a time and speed program. Sensors monitor viscosity, temperature, and mixing torque to determine completion. The mixing cycle is designed to develop a consistent batter texture while minimizing gluten overdevelopment. Most muffins use the muffin method, where liquids and dries are blended quickly with minimal agitation. The final batter is thick, glossy, and aerated. Scraper blades clean the sidewalls of the mixing bowl continuously to ensure uniformity throughout the mix. Once mixing is complete, the batter is pumped into an intermediate holding hopper. These hoppers are jacketed to maintain temperature, typically between 18 degrees Celsius and 26 degrees Celsius, and feature slow-speed agitators to prevent separation. The batter is held under light pressure to feed the depositors efficiently and without introducing excess air. Meanwhile, paper muffin cups are dispensed into baking trays by a cup denister. Trays are made from perforated metal or non-stick coated aluminum, often holding 12 to 24 cavities per tray. The trays travel along a conveyor system toward the depositing zone. As each tray enters the depositor station, it is precisely indexed into place by servo-controlled gates. Batter is deposited using multi-nozzle volumetric piston depositors. These depositors operate with individual cylinders that draw and dispense set volumes of batter into each cup. Fill weights are carefully calibrated, typically between 50 and 120 grams per muffin, depending on product specifications. Tolerances are within plus 1.5 grams. Deposit profiles can be circular, spiral, or domed, depending on desired peak structure. Depositor heads are adjustable in height and spacing allowing format changes without complete tooling replacement. For muffins with inclusions, such as blueberries, chocolate chips, or nuts, an ingredient dosing unit integrates with the depositor. Inclusions are metered into the batter just before deposition to prevent sinking or damage during mixing. The distribution system uses augers or vibration channels to deliver equal portions into each cup, either layered or blended depending on recipe. Optional toppings are applied at this stage. Streusel, sugar crystals, seeds, or flavored crumbles are dropped by overhead sprinklers or belt feeders. These systems are synchronized with tray motion, using vision sensors to detect cup position and deliver toppings directly onto the surface of each batter portion. Filled trays proceed to the oven. Industrial tunnel ovens, either gas-fired or electric, bake muffins continuously. The oven conveyor moves at a speed determined by product size and bake profile, typically yielding a dwell time of 12 to 18 minutes. Oven zones are independently controlled for top and bottom heat, with precise air circulation to ensure even baking. Core product temperature is monitored using inline thermocouples that pierce random samples. Exit temperature targets typically range from 93 degrees Cs to 98 degrees Cs. Inside the oven, batter rises due to the activation of chemical leavening agents. Steam forms from the water and egg content, expanding air cells and lifting the batter upward. As proteins coagulate and starches gelatinize, the muffin structure is set. Surface coloration and crust formation are controlled by air humidity and sugar content. Once baked, trays exit the oven onto a cooling conveyor. This conveyor is long enough to allow the muffins to cool from above 90 degrees Celsius down to ambient room temperature, usually within 20 to 30 minutes. High volume air blowers accelerate heat dissipation. Muffins remain in their trays during this time to retain shape and prevent sticking to belts. After cooling, muffins are depanned. A pneumatic or mechanical depanner inverts the tray and applies a brief vacuum or finger push to lift each muffin out. The muffin cups remain intact, and the products are transferred onto a belt for inspection. Empty trays are returned via overhead conveyors or underbelt returns to the cup denesting station for reuse. Muffins are now inspected by a vision system. Cameras mounted above and to the side scan each muffin for volume, surface cracks, peak height, and alignment in the paper cup. Any product that falls outside the specification window is diverted by a mechanical pusher or drop gate. Approved muffins continue to the A packaging zone. Packaging formats vary depending on customer needs. Muffins can be individually wrapped, packed in clamshell trays, or sealed into multi-packs. For individual wrapping, muffins are fed into a flow wrapping line. Each muffin enters a forming collar, where film is wrapped around it and sealed using heated rotary crimpers. Longitudinal and cross seals are made with controlled temperature and pressure. Speeds can reach up to 300 muffins per minute per line. For clamshell packing, muffins are guided into a colada, where robotic pick and place arms grip each unit and place it into thermoformed PT trays. These trays are then lidded and sealed with tamper-evident films or snap-on covers. Date and batch codes are printed using thermal inkjet printers. For bulk or food service formats, muffins are loaded into cardboard display trays or placed directly into polyethylene-lined cartons. Cartons are erected from flat blanks using a box erector. Muffins are loaded in rows, either manually assisted or robotically, and the carton is then closed with hot melt adhesive and conveyed toward the palletizer. At the palletizing station, robotic arms equipped with vacuum grippers or mechanical forks stack cartons onto wooden or plastic pallets. Patterns are selected based on case size and distribution route. Slip sheets are inserted every few layers for stability. Finished pallets are stretch wrapped by a rotating arm system and labeled with barcodes and shipping data. All production steps are integrated into a plant-wide control system. Programmable logic controllers coordinate each machine, while SCADA systems provide real-time data on batch progress, line speed, machine temperature, deposit weight, oven humidity, and output count. Operators monitor the entire line from centralized terminals, adjusting set points and diagnosing faults without stopping the process. Ingredient traceability is managed through automated lot tracking. Each ingredient batch is scanned upon entry and linked digitally to every production batch. Finished goods are barcoded and traced back through mixing, depositing, and baking history. If a deviation occurs, the system flags affected pallets and isolates them immediately. Cleaning is performed through a mix of clean in place and clean out of place protocols. Mixing tanks, pipes, depositors, and pump systems are flushed with alkaline detergent followed by a hot water rinse. Baking trays and conveyors are cleaned with steam or dry brushing. Nozzle heads and sensor lenses are wiped with food-safe solvent solutions. Environmental conditions are tightly controlled. The mixing room is temperature stabilized to avoid batter inconsistency. The depositing area uses filtered air to keep particles off open trays. Oven exhaust is captured and scrubbed. Packaging areas are overpressurized with filtered air to minimize dust entry. Air knives and vacuum hoods remove crumbs during transfer points. If muffins are frozen, post-production, they are conveyed directly into a spiral freezer. Cold air at 35 degrees Celsius rapidly reduces product temperature to below 18 degrees Celsius within 30 minutes. Frozen muffins are then flow wrapped or shrink wrapped in bulk, palletized, and moved into cold storage. The entire process is timed to avoid moisture condensation and surface bloom. Shape consistency is enforced at multiple stages. During depositing, laser sensors measure batter height. Post-baking, peak height and crown diameter are scanned optically. Deformed or underfilled units are rejected before reaching packaging. Automated systems collect real-time statistics to maintain statistical process control. The production line is modular. Deposit heads, paper cup sizes, and topping applicators can be changed within minutes. Oven belts, mixing times, and wrap formats are selected through the control interface. Recipe memory allows for instant switchovers without manual recalibration. Muffin factories operate continuously, running multiple shifts with minimal stoppages. High-volume lines produce tens of thousands of muffins per hour. Every unit is created through thermal transformation, timed chemistry, pneumatic forming, and servo-synchronized packaging. Every process step is calibrated, controlled, and monitored to meet exact physical and sensory specifications. The factory production of chocolate chip cookies begins with the bulk delivery of essential raw ingredients. These include wheat flour, white and brown sugars, vegetable shortening or butter substitute, liquid eggs or pasteurized egg products, chocolate chips, leavening agents, salt, emulsifiers, water, and flavorings such as vanilla. Dry ingredients like flour and sugar arrive in super sacks or silo containers and are transferred pneumatically or via screw conveyors into batching silos. Liquid ingredients are stored in temperature-controlled stainless steel tanks connected to dosing lines. Chocolate chips are stored in insulated bins and gently agitated to prevent compaction or melting. Automated ingredient handling systems prepare each batch according to a programmed recipe. The process begins in the scaling room or dosing station, where load cells measure and release precise amounts of dry and wet ingredients into transport hoppers. Materials are conveyed into a high-capacity horizontal mixer, typically of the ribbon or paddle variety. These mixers are equipped with dual-axis blades and variable speed motors. Ingredients are added in a fixed sequence. Fats and sugars first to cream, then eggs and water, followed by dry powders, and finally chocolate chips. Mixing proceeds through defined phases. During the creaming phase, Sugar granules break down the fat, creating air pockets essential for cookie spread and tenderness. The incorporation of eggs and water creates an emulsion that stabilizes the dough. As flour and leavening agents are added, the blades slow down to avoid overdevelopment of gluten. The chocolate chips are added last and folded gently to prevent breakage. Inline torque sensors monitor dough consistency, and viscosity meters verify proper development. Batch temperatures are maintained between 18 degrees Celsius and 24 degrees Celsius to prevent fat melt and preserve dough structure. Once mixed, the dough is transferred into a hopper positioned above the forming line. Dough moves via auger or vacuum feed into a volumetric portioning system. A rotary cutter or wire cut depositor divides the dough into individual pieces, each weighing between 25 and 50 grams, depending on the product specification. The depositor uses servo-driven pistons to extrude dough pieces onto a moving steel mesh or Teflon-coated band conveyor. Optical sensors monitor spacing, alignment, and shape, correcting for drift in real time. For wire-cut lines, dough is pushed through nozzles and sliced cleanly by a fast-moving wire as the band advances. For rotary molded formats, dough is pressed into engraved molds on a rotating drum, then released onto the band using a flexible scraper blade. Shape, weight, and chip distribution are confirmed by an overhead vision inspection system using laser profiling and high-speed imaging. Defective pieces are automatically rejected via air puffs or diverter gates. Decorative or functional toppings, such as extra chocolate chips, coarse sugar, or sea salt, can be added before baking. These are applied using vibratory feeders or pneumatic dispensers, synchronized with the conveyor speed. Toppings are placed with positional accuracy, controlled by encoder feedback. The unbaked cookies enter the oven on a continuous conveyor. Most large-scale bakeries use tunnel ovens ranging from 25 to 60 meters in length. Ovens may be gas-fired, electric, or hybrid, and are divided into multiple heating zones. Each zone has independently controlled top and bottom heating elements, recirculating fans, and steam injection systems. Bake times range from 6 to 12 minutes, depending on cookie size, dough moisture, and desired texture. As cookies pass through the oven, heat activates the leavening agents, causing the dough to expand. Water turns to steam, fats melt, and proteins begin to coagulate. Sugars caramelize on the surface, contributing to flavor and browning. Top heat ensures color formation, while bottom heat ensures base firmness. An inline thermal imaging system monitors surface temperature and identifies any uneven baking. Oven humidity is also regulated to manage cookie moisture and bite texture. After baking, cookies exit the oven at internal temperatures above 90 degrees Celsius. They are transferred to a multi-tiered cooling conveyor that spans 20 to 40 meters in length. Cool ambient air is blown across the surface of the cookies to gradually reduce their temperature to 30 degrees or lower. The cooling line uses stainless steel or open mesh plastic belts to allow airflow from above and below. Rapid cooling is avoided to prevent cracking or structural collapse. Crumb blowers and air knives remove any loose particles generated during baking. Once cooled, cookies pass through a final inspection station. A high-speed vision system checks each unit for diameter, thickness, browning level, chip exposure, and edge uniformity. Any cookie failing the inspection parameters is ejected automatically. Passing cookies proceed to the packaging section. Depending on the final format, cookies may be packed in flow wrap, trays, clamshells, or flexible pouches. For flow wrap, cookies are aligned single file by a lane guide and transferred onto film. Film is unwound from a roll, cut to length, and wrapped around each cookie. Heat sealing jaws close the ends and form a longitudinal seam. Wrapping speeds can exceed 500 cookies per minute per lane. For tray packing, cookies are collated into rows by a bucket conveyor and placed into pre-formed plastic or paperboard trays by robotic pickers. In multi-pack formats, cookies are stacked vertically or nested side by side using servo-driven stackers. These stacks are inserted into pouches or boxes that are formed, filled, and sealed in a continuous motion machine. Machines apply nitrogen flush to pouches before sealing to displace oxygen and extend shelf life. Date codes and batch numbers are applied using thermal inkjet printers or laser coders. Barcodes are printed for inventory and traceability. Wrapped products are collated into cartons by robotic arms equipped with suction grippers. Cartons are sealed with hot melt glue and stacked onto pallets in pre-programmed patterns. Palletizers use multi-axis robots with slip sheet dispensers to build stable, shippable loads. Pallets are conveyed to a stretch wrapper where they are secured with plastic film. Labels with tracking codes and distribution information are applied before pallets are moved to dispatch or cold storage. All stages of production are monitored and controlled by a centralized PLC-based automation system. The entire factory line is integrated through SCADA interfaces that provide operators with real-time dashboards showing mixer status, dough temperature, line speed, oven zone profiles, moisture content, wrapping rate, and defect counts. Recipe management software ensures every batch conforms to specification and every change is logged digitally. Clean-in-place systems are used for all dough contact equipment. After production, mixers, hoppers, pipelines, and depositors are flushed with food-safe detergent and rinsed with hot water. Belt surfaces are cleaned with steam or sanitizing solution and scraped with mechanical blades. Oven interiors are brushed and vacuumed between shifts to remove carbonized residue. Environmental conditions like air pressure, temperature, and humidity are tightly controlled in all processing zones to prevent microbial growth and maintain dough stability. Ingredient traceability is maintained through barcode scanning and batch logging. Each input is recorded upon arrival and linked to its corresponding finished batch. If any quality issue is detected downstream, affected products can be isolated immediately through backtracking. Quality assurance teams conduct routine sampling, including water activity, texture, chip dispersion, packaging seal integrity, and shelf life simulations in controlled chambers. Some facilities operate in robing lines for chocolate-dipped or striped cookies. These cookies exit the oven and are passed through a tempering tunnel where they receive a coating of milk, dark, or white chocolate. The coating is applied using cascading curtains or rotating drums, followed by a cooling tunnel with airflow designed to produce a glossy finish and stable crystallization. Other variants include filled cookies, where dough is extruded with a central cavity filled with chocolate paste, caramel, or fruit gel. These are formed using a co-extrusion head that aligns both dough and filling. The filled ropes are cut by guillotine or rotary blades and shaped prior to baking. Additional vision inspection ensures filling is centered and not leaking. Pepsi begins with water, ordinary in origin, but transformed through an intense purification system. First, the water flows through mechanical filters, stripping out any visible particles. It moves next into activated carbon beds, where chlorine, organic residues, and odors are removed. Then it's pushed through reverse osmosis membranes under high pressure, leaving behind salts, microbes, and trace contaminants. A final sweep of ultraviolet light and ozone leaves the water sterile, mineral-free, and chemically neutral. This is the blank canvas. The next stage injects character. Deep inside jacketed mixing tanks, a thick amber concentrate is created. Liquid sugar surges through stainless steel lines into the tank, met by metered doses of colorants, acids, caffeine solution, and the core flavor compound. Inside the vessel, high-speed impellers shear the mixture into uniformity. The liquid darkens, thickens, and becomes the syrup that defines the drink's signature base. Flow meters and refractometers verify sugar density to the decimal. Agitators spin in controlled bursts. A small shift in temperature or pH would trigger instant correction by the automated control system. Once blended, the syrup doesn't wait. It flows straight into a proportioning unit, where it meets the ultra-purified water. Two pressurized lines merge into one, and precisely tuned valves blend them in a 5-to-1 ratio. The new mixture forms a complete beverage. Almost. First, it's sprayed into a vacuum chamber. This fine mist encounters low pressure and a cloud of CO2. Oxygen is stripped away. The liquid is chilled rapidly to near freezing, lowering its ability to resist carbonation. Inside the carbonation vessel, thousands of microscopic pores inject CO2 with exact pressure. The liquid churns gently in a sealed chamber, held under 4 bar of pressure at 0 to 2 degrees Celsius. Gas dissolves silently. Bubble size, saturation rate, and temperature are monitored in real time. When carbonation reaches target levels, the drink exits the vessel with all of its effervescence locked in. On another line, PET bottle preforms arrive in rapid succession. Each one is gripped by a rotary arm and passed through infrared heaters. The plastic softens and glows dull red before entering the blow mold cavity. High-pressure air inflates it in a fraction of a second, pressing it against the steel mold's walls to form a full-size bottle, contoured, clear, and warm to the touch. It exits the mold and cools on contact with the conveyor air. Bottles enter the rinsing carousel, where they're inverted and blasted internally with sterilized water. As they flip upright again, air knives dry the insides instantly. Next, they move toward the isobaric filler, a rotary machine that maintains pressure equilibrium between the drink and the container. Each bottle is clamped beneath a filling valve. CO2 gas is injected first to pressurize the empty space. Then the valve opens, and the drink enters from the base, rising smoothly with minimal turbulence. Foam is avoided. Gas is preserved. The moment filling is complete, the bottles roll to the capper. Here, precision torque heads spin blue caps onto each neck. A magnetic clutch delivers exact closing force, tight enough to seal, loose enough to open later. Inline torque sensors confirm every closure. Any outliers are ejected instantly by a compressed air nozzle. From there, each sealed bottle passes under a jet printer that marks it with time, date, and batch code. The ink dries in under a second. A vision system verifies code presence and clarity. Another camera checks fill level and cap alignment. Each bottle is under constant scrutiny as it moves down the line at hundreds per minute. Labels come next. A roll-fed applicator unwinds pre-printed film and cuts each label to size. As bottles spin past, a roller applies adhesive, wraps the label, and smooths it with a brush. The result is a seamless, wrinkle-free appearance with perfect alignment. Sensors detect any offset and make micro-adjustments on the fly. Now grouped into formation, the bottles move toward bundling. A collator arranges them into packs, 6, 12, or 24, depending on the format. Shrink film is draped over each group and heat sealed at the seams. The entire bundle then passes through a shrink tunnel where hot air circulates in tight zones. The film tightens instantly, locking the bottles together in a rigid block. Bundled packs exit the tunnel and head for palletizing. Robotic arms swing overhead, guided by vision cameras and programmed stacking patterns. Grippers lift multiple bundles at once and layer them on wooden pallets. Slip sheets are inserted between tiers by a vacuum-fed arm. Once stacked, the entire pallet is conveyed into a stretch wrapper. A rotating arm winds clear film around the stack in tight spirals, binding the load into one secure shipping unit. Meanwhile, cans run on a parallel line. Massive depalletizers feed columns of aluminum cans into a rinsing tower. From there, the empty cans travel into another isobaric filler designed specifically for pressurized metal packaging. Liquid fills the cans from the bottom. A seamer spins down a lid, hooks the metal under the rim, and crimps it tight. A double seam forms, locking the gas inside with extreme precision. Cans are inverted, jet-coated, vision inspected, and shrink-wrapped in trays. Robotic stackers build them into pallet loads at similar speed to the bottle line. Both packaging lines converge in the same warehouse zone, where outbound conveyors feed the finished pallets toward refrigerated staging docks. Each section of the line is governed by PLCs. These controllers monitor temperature, fill height, carbonation levels, syrup ratios, and packaging counts. Real-time data appears on SCADA terminals, allowing operators to adjust line speed, diagnose faults, and fine-tune performance without stopping production. If any parameter drifts out of tolerance, such as syrup bricks, carbonation pressure, or label alignment, the system either autocorrects or halts the affected module. Clean-in-place systems activate between product runs. Valves switch flow from production mode to cleaning mode. Heated alkaline solution flushes through all contact surfaces, syrup tanks, filler bowls, carbonators, valves, and pipes. Sensors track flow rate and chemical concentration. After the caustic wash, a water rinse clears residue, followed by a sanitizing flush. No disassembly is required. The entire cleaning cycle is automated and logged. During operation, bottle speeds exceed 60,000 units per hour. Carbonation tanks maintain saturation levels within plus 0.05 volumes. Fill levels are accurate to within plus and 1.5 milliliters. Every step, from syrup blending to cap torque, is governed by tolerances and feedback loops. When the process runs at full speed, hundreds of meters of conveyor synchronize bottle spacing, curve speed, and back pressure control. Star wheels, diverters, and sensors ensure smooth flow with no collisions. Air conveyors keep lightweight empty bottles suspended and aligned without touching mechanical guides. Pepsi's production system is built for non-stop performance. Each component, carbonator, blow molder, labeler, filler, capper, bundler, is modular and servo-driven. Changeovers for different bottle sizes or formats require only a software switch, a tooling exchange, and a calibration cycle. The entire system adapts to new production schedules without downtime. Fanta production starts with water, but it cannot be ordinary. The raw supply flows into a filtration system where coarse particles are stripped away. From there, the water passes through activated carbon beds to remove chlorine and organic traces. Next, it enters a reverse osmosis membrane under pressure, separating out salts, metals, and microbes. At this stage, the water is nearly sterile. A final ultraviolet treatment and ozone injection complete the purification. Now the water is neutral, flavorless, and ready for transformation. Inside a stainless steel mixing tank, the drinks base is constructed. A stream of refined liquid sugar is pumped in through insulated lines. Dosing pumps feed in controlled quantities of citric acid, natural fruit flavors, stabilizers, preservatives, and vibrant colorants. The tank's agitators rotate at set intervals to blend the ingredients evenly. Every element is added with exactitude. Flow meters regulate sugar volume. Acid concentration is tracked by inline pH sensors. Color intensity is verified with optical density readers. The mixture is continuously monitored for consistency. Temperature is held between 15 and 20 degrees Celsius. If any reading deviates from target, the control system halts the process and recalibrates dosing in real time. Once the syrup reaches specification, it is transferred to a buffer tank where it rests briefly under agitation, held at a constant temperature and protected from ambient air. Next, the beverage is formed through a high-speed proportioning system. The syrup is combined with the purified water in a fixed ratio, generally around 1 part syrup to 5 parts water. This is managed by synchronized flow meters and control valves. The blending occurs in line, with turbulence in a stainless steel chamber, ensuring rapid and even mixing. The liquid then flows into a deaeration unit. Inside this sealed vessel, the drink is atomized into fine droplets under vacuum. Dissolved oxygen is extracted while carbon dioxide is introduced. This prevents oxidation, preserves flavor integrity, and prepares the drink for carbonation. Carbonation takes place in a pressurized tank known as the carbonator. Here, the chilled beverage is exposed to a steady stream of carbon dioxide gas. The pressure inside is typically maintained at 3 to 4 bar, and the liquid temperature is kept just above 0 degrees Celsius. These conditions maximize CO2 solubility. Porous stones or fine nozzles distribute the gas, ensuring uniform saturation throughout the tank. Agitators gently rotate to avoid stratification while preventing bubble escape. Meanwhile, packaging lines are activated. If plastic bottles are manufactured on site, polyethylene terephthalate preforms are loaded into a rotary feeder. Each preform is gripped and passed through an infrared heating oven, where the plastic softens. Inside a blow mold cavity, the preform is inflated with high pressure air into its final shape. Bottles emerge, fully formed and warm to the touch. Air conveyors guide them toward rinsing. Rinsers invert each bottle and spray sterile water into the interior. The bottles are then dried with air knives and positioned upright for filling. They enter a rotary isobaric filler, where pressure is equalized between the bottle and the drink to preserve carbonation. Each bottle is locked into a filling valve. First, carbon dioxide gas purges the empty space, preventing oxygen contamination. Then the valve opens and the carbonated Fanta flows upward from the base. Foam is avoided through bottom-up filling and controlled turbulence. When the fill line is reached, the valve shuts instantly. Excess gas is vented and the bottle is released onto the next conveyor. Caps arrive from a centrifugal sorting bowl. They are aligned, sanitized, and fed toward the capper, where a torque head presses and twists each one onto the bottleneck. The torque is monitored by a feedback sensor that checks every closure in real time. Any bottle that fails to meet torque specs is diverted automatically from the line. A high-speed inkjet printer then marks each bottle with production codes, timestamps, and batch identification. These markings are inspected by vision systems that confirm legibility and placement. Additional cameras check fill height and cap alignment. Bottles failing any inspection are rejected through pneumatic actuators. Labeling follows. A roll-fed labeler applies either pressure-sensitive or glue-applied labels depending on the format. The label roll unwinds, cuts to length, and wraps each bottle in a single smooth motion. Rollers press out any air bubbles, and sensors verify label position. Adjustments are made automatically based on visual feedback. Labeled bottles are grouped into packs at the bundling station. A servo-controlled collator arranges them into 12s, 6s, or 24s depending on product format. A plastic shrink film wraps around the group, and the pack passes through a heat tunnel. Hot air shrinks the film tightly, locking the bottles into a unified pack. The packs move on to palletizing. A robotic arm with suction cups or mechanical clamps picks up each bundle and stacks it on a pallet in alternating patterns. Slip sheets are added for stability. Once a pallet is full, it's moved into a stretch wrapper. A rotating arm wraps plastic film under tension from the base to the top of the stack. This secures the load for transport. Parallel to the bottle line, aluminum cans are processed on a separate track. Empty cans arrive by depalletizer and enter a rinser. After internal cleaning, they flow into a high-speed rotary filler. Isobaric pressure filling minimizes gas loss. Immediately after filling, the cans pass into a seamer where a metal lid is dropped and double seamed with extreme force and precision, sealing in the carbonation. Cans are coated, checked, and shrink wrapped into trays, then palletized, just like bottles. Every mechanical step is governed by programmable logic controllers. These devices receive data from sensors monitoring flow rates, temperatures, torque values, fill levels, and carbonation pressure. If any parameter drifts beyond tolerance, the system adjusts in real time or stops the line. All systems communicate through a central SCADA interface, which displays status updates, alarm logs, and production metrics. Carbon dioxide is supplied from insulated bulk tanks located outside the plant. The gas enters the process through a vaporizer and filtration unit. Inline pressure regulators and flow restrictors ensure stable CO2 supply at all stages, from de-aeration to final carbonation. Clean-in-place systems activate between production cycles. A series of automated valves switch flow from product to detergent solution. Heated caustic cleans the tanks, pipes, carbonator, and filler valves. A rinse follows, and finally, a sanitizing solution is circulated. No disassembly is required. The process is monitored by conductivity meters and temperature sensors to verify cleaning effectiveness. Each segment of the Fanta production line is built for modularity and speed. Conveyor belts stretch across the plant in smooth arcs, synchronized by servo motors. Air conveyors are used in bottle transport to prevent mechanical contact. Accumulation zones between machines allow buffer space, so the line continues running even if one unit slows down. Production speeds for bottles can exceed 60,000 units per hour. Lines can operate at over 120,000 units per hour. The entire system is balanced to prevent bottlenecks. Fillers, labelers, and palletizers adjust their speed based on feedback from downstream equipment. Fill level is controlled to within 1.5 milliliters. Carbonation is regulated within a tolerance of 0.05 volumes of gas. Cap torque is checked to within 1 Newton meter. These tolerances are enforced by constant feedback and precision sensors. Label alignment is maintained through optical recognition. If the label wanders off-center by more than 2 millimeters, the labeler adjusts roller speed and cutter timing. Bundling film is tension controlled to avoid wrinkles or tears. Shrink tunnels have multi-zone heating, each controlled by thermocouples. Fanta's bright appearance comes from precise color dosing. The colorant solution is metered by mass flow controllers that inject it directly into the syrup blend. Any deviation in hue is detected by an inline spectrophotometer. For different flavors and regions, flavor concentrate tanks are changed out through quick connect valves. Each tank is barcoded, and the system will not run unless the correct flavor for the scheduled run is confirmed. All ingredient additions are logged, time-stamped, and tracked through the control network. Dr. Pepper begins with purified water. Municipal or well-sourced, the incoming supply is routed through a multi-stage treatment system. First, it flows through coarse filters that remove sediments and suspended particles. Then it enters activated carbon beds, which strip chlorine, off flavors, and organic traces from the water. Next, the liquid is pumped through a reverse osmosis membrane under high pressure. This removes dissolved minerals, bacteria, and microscopic contaminants. Final disinfection is completed using ultraviolet light and ozone. The result is neutral, sterile water, continuously recirculated through stainless steel holding tanks to maintain freshness and prevent stagnation. Inside the syrup room, Dr. Pepper's base formula is built in a precision blending tank. Liquid sugar, delivered in insulated tankers, is pumped into the tank through flow-regulated stainless lines. Into this stream, concentrated acids, natural and artificial flavors, colorants, and preservatives are dosed through servo-driven valves. These ingredients are not added all at once, but follow a timed sequence governed by a central control, System. Stirring paddles agitate the mixture at programmable speeds. Viscosity sensors monitor the syrup's thickness. A pH probe verifies acid levels. An inline refractometer measures sugar concentration down to 1/10 of a Brix unit. As the mixture blends, the syrup's consistency is adjusted by adding chilled water or holding the solution under vacuum to prevent oxidation. Dr. Pepper's distinct flavor comes from a complex mix of flavor oils and acids, blended in sub-milliliter quantities by a dedicated dosing module with flow control down to microliters. Once all parameters are within specification, the syrup is held in a buffer tank under sealed conditions, continuously stirred and maintained at a stable temperature. Syrup is then piped into a proportioning unit where it meets the purified water in exact ratios. Typically, 1 part syrup is mixed with 5 parts water. Flow meters and precision control valves adjust the inputs in real time, ensuring consistency throughout the production run. This mixing takes place inside a turbulence chamber designed for immediate homogenization. The freshly blended beverage passes through a deaeration chamber. Here, the liquid is atomized under vacuum, breaking it into tiny droplets. This process removes dissolved oxygen that would otherwise cause off flavors or affect carbonation retention. Simultaneously, carbon dioxide gas is injected into the chamber to further displace any remaining oxygen. The temperature is dropped below 5 degrees Celsius to prepare the drink for carbonation. Carbonation takes place in a pressurized stainless tank fitted with high-efficiency gas diffusers. The beverage is injected with food-grade carbon dioxide at controlled flow rates. Pressure is held steady between 3 and 4 bar, while temperature is maintained just above freezing. Agitators inside the tank rotate slowly, ensuring uniform CO2 saturation without causing foaming or loss of gas. Carbonation level is verified with an inline CO2 analyzer calibrated to within 0.05 volumes of gas. While the beverage is being carbonated, packaging operations are running in parallel. On the bottle line, polyethylene terephthalate preforms are fed into a rotary blow molder. Each preform is picked up by a gripper arm and passed through infrared heaters. When the plastic softens to the ideal temperature, it is transferred into a mold. High-pressure air inflates it rapidly, pressing it into the mold cavity and forming the final bottle shape. The molded bottle is immediately cooled and conveyed onward by air track systems that minimize surface contact. At the rinsing station, bottles are inverted and blasted with sterile water or filtered compressed air. After rinsing, the bottles are uprighted and fed into an isobaric rotary filler. This machine equalizes the internal pressure of the bottle with that of the carbonated beverage, minimizing gas loss during filling. Each bottle is clamped into a filling turret. A burst of CO2 is injected first to displace any residual air. Then the valve opens and liquid enters from the bottom. As the beverage level rises, gas is displaced upward and captured. Fill level sensors detect the target point, and the valve shuts instantly. The bottle rotates out and moves to the capping unit. Caps are sorted and oriented by centrifugal feeders. They are sterilized in line and delivered to the capping head, where servo-driven torque applicators screw them onto the bottleneck. Torque is measured in real time. Each closure is verified for tightness and alignment. If torque deviates from specification, the bottle is automatically rejected. After capping, the bottles move under an inkjet printer. Here, date codes, batch numbers, and production timestamps are applied to the shoulder or neck of the bottle. High-resolution cameras inspect the print for clarity and accuracy. Another vision system scans the bottle for correct fill level, cap integrity, and label presence. Labeling occurs at high speed. Rolls of pre-printed labels are fed into a rotary applicator. As each bottle rotates past, a servo-controlled arm presses the label onto the surface using adhesive or heat. Rollers smooth the label edge to edge. A laser eye checks label alignment and triggers adjustments if needed. Labeled bottles are grouped at the bundling section. Depending on the product format, bottles are organized into groups of 6, 12, or 24. A clear shrink film wraps the cluster, and the bundle moves through a hot air tunnel. Controlled heating zones shrink the film tightly around the bottles without warping or melting. Next, the shrink-wrapped bundles are transported to the palletizing area. A robotic arm equipped with vacuum grippers picks up each bundle and stacks it onto a pallet following a programmed pattern. Slip sheets are inserted between layers to add friction and prevent collapse during transport. Once the pallet is complete, it is conveyed to a stretch wrapper. A rotating arm encircles it, applying plastic film from bottom to top. Film tension is automatically adjusted based on load profile and height. Parallel to the bottle line, the can line operates with higher throughput. Empty aluminum cans are depalletized and fed into a high-speed rinsing tower. After rinsing, cans enter a rotary filler similar to the one used for bottles, but designed specifically for metal packaging. The carbonated Dr. Pepper is injected under pressure. Immediately afterward, lids are placed on the cans and sealed with a double seamer. This forms an airtight seal between the lid and the can body. Cans are inverted, coated with inkjet printers, and inspected by a multi-camera system. Approved cans are organized into trays or shrink-wrapped into multi-packs. Robotic palletizers stack the finished units onto pallets. Final pallets are labeled, wrapped, and staged for shipping. Throughout the process, programmable logic controllers coordinate every movement. Each section of the line operates independently but communicates through the central control system. SCADA terminals show live readouts of temperature, pressure, line speed, fill volume, syrup ratio, carbonation level, and product counts. Alarms and trend logs are automatically stored for quality assurance. Carbon dioxide is supplied from an external cryogenic tank. The liquid gas is vaporized and filtered before entering the production system. Flow meters and pressure regulators maintain steady gas delivery to the de-aeration and carbonation units. Backup systems ensure uninterrupted flow. Clean-in-place systems operate at the end of each production run. Automated valves redirect flow through all product contact surfaces. Heated caustic detergent is pumped through tanks, pipes, fillers, and carbonators. A water rinse follows, and then a sanitizing solution is circulated. Conductivity and temperature sensors confirm cleaning efficiency. The entire cleaning sequence is logged and time-stamped. Dr. Pepper production lines are built for speed and adaptability. The blow molder can be adjusted for different bottle volumes. The labeler and filler can switch formats through software changes and tool-free part swaps. Servo motors drive most critical systems, allowing rapid changeovers with high accuracy. Filling accuracy is controlled to within 1.5 milliliters per container. Carbonation tolerance is held within 0.05 volumes of CO2. Cap torque is measured to within a fraction of a Newton meter. Label alignment deviation is limited to 2 millimeters. Every product is subjected to multiple points of verification before it leaves the line. Accumulators between machines allow for variable speed balancing. If a downstream unit slows, upstream conveyors store excess product temporarily. This prevents system shutdowns and maintains steady throughput. Conveyors are fitted with contactless sensors that monitor spacing and position, allowing real-time speed adjustment without collisions or jams. From raw water intake to final pallet wrapping, every phase of Dr. Pepper production is controlled, calibrated, and continuously monitored. No step is isolated. Syrup formulation, carbonation, filling, labeling, coding, packaging, and palletizing are integrated into a seamless flow of motion, temperature, pressure, and precision. Red Bull starts with its formula. a carefully guarded blend of ingredients that deliver its characteristic taste, texture, and functional effects. At the heart of the recipe is water, which serves as the main ingredient by volume. This water is not simply pumped from a municipal source and used directly. It undergoes multiple purification stages to ensure it is free of any dissolved solids, minerals, or microorganisms that might alter the taste or stability of the drink. The purification typically begins with coarse filtration to remove particulate matter, followed by activated carbon filtration to strip out organic compounds and chlorine, then reverse osmosis to achieve a very low mineral content. The final step often involves ultraviolet light treatment or ozonation to sterilize the water before it enters the production tanks. Once the water is ready, the remaining ingredients are prepared. These include sucrose and glucose for sweetness and energy, citric acid for acidity and flavor balance, taurine as a functional amino acid, caffeine as the stimulant, and B group vitamins like niacinamide pantothenic acid, vitamin B6, and vitamin B12. Each of these arrives at the factory in bulk form. Sugars as fine crystals, taurine and caffeine as purified powders, vitamins as either powders or highly concentrated solutions. All are stored under controlled conditions and tested in an in-house quality lab for purity and potency. The creation of the beverage begins with the preparation of a concentrated syrup. In large stainless steel blending vessels, precise amounts of sugar are dissolved in purified water under gentle heat, usually between 50 and 60 degrees Celsius, to speed dissolution without caramelizing the sugar. The glucose syrup, if used in liquid form, is pumped directly into the blending vessel through sanitary pipelines. Once the sugars are fully dissolved, the other functional ingredients, taurine, caffeine, and vitamins, are added in carefully measured doses. This mixing process is critical. Operators rely on automated ingredient dosing systems connected to load cells and flow meters to ensure exact quantities, as even a small deviation could alter flavor or regulatory compliance. Citric acid is then introduced to adjust the pH, giving Red Bull its slightly tart backbone and enhancing stability. Flavors, which are part of a proprietary blend, are also incorporated at this stage. These may include natural and artificial components that together create the drink's distinctive aroma and taste. The mixing tanks are fitted with high-speed agitators to ensure uniform distribution of all ingredients, and the resulting syrup is tested in the lab for Brix, acidity, and flavor profile before moving forward. Once the base syrup is complete, it is diluted with more purified water to bring it to the target concentration for the finished beverage. This final liquid mixture, now containing all flavor and functional components, is chilled to prepare it for carbonation. Carbonation is one of the defining aspects of Red Bull's sensory experience, and it is performed with great precision. The chilled beverage passes through a carbonator where it is brought into contact with carbon dioxide under high pressure. The CO2 dissolves into the liquid with the level carefully controlled. Too little carbonation would make the drink taste flat, while too much could affect mouthfeel or cause excessive foaming during filling. The carbonated beverage is then immediately directed to the filling lines. Red Bull is packaged almost exclusively in aluminum cans, chosen for their lightweight nature, excellent barrier properties against light and oxygen, and recyclability. These cans arrive at the factory in massive stacks of unprinted or pre-printed containers, each one spotless and free from dents or imperfections. Before filling, they undergo a thorough rinse with deionized water or ionized air to remove any dust or debris. The rinsed cans move down the line on high-speed conveyors into the filling carousels. The filling process operates at incredible speed, often hundreds of cans per minute, and is performed in a pressurized environment to maintain carbonation. Each can is filled from the bottom up to minimize turbulence and foaming, then immediately sealed with an aluminum end by a seaming machine. This seam is a precision crimping of the lid to the can body, creating an airtight and watertight seal. Once sealed, each can is inverted briefly to ensure the lid is fully sanitized by contact with the beverage inside, then returned upright. Immediately after sealing, cans pass through automated inspection systems. These use a combination of cameras, sensors, and weight checks to identify any underfilled, overfilled, or defective cans. Any can that fails inspection is automatically rejected and diverted from the main conveyor. Approved cans move on to pasteurization or cold sterilization, depending on the plant's process design. Pasteurization involves heating the cans to a specific temperature for a set time to ensure microbial stability, while cold sterilization uses aseptic filling combined with sterilized containers to achieve the same result without heat. Once the cans are confirmed safe and stable, they head to the secondary packaging area. Here, they are grouped into the familiar 4-packs, 6-packs, or larger cases using cardboard wrap or shrink film. Automated cartoners or shrink wrappers handle this at high speed, often in combination with robotic case packers that load the multi-packs into corrugated shipping cases. The shipping cases are sealed with tape or hot melt glue, coated with batch information for traceability, and then stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability and transported to a climate-controlled warehouse. Although Red Bull is shelf-stable at room temperature, storage away from excessive heat or direct sunlight helps maintain carbonation and flavor over time. From the warehouse, pallets are loaded onto trucks bound for distribution centers and retailers. Given Red Bull's global reach, many of these pallets also enter intermodal shipping containers for transport by rail or sea to other countries. Throughout production, the emphasis on quality and consistency is relentless. Every batch of syrup and finished beverage undergoes analytical testing to confirm caffeine content, vitamin levels, acidity, and carbonation. Sensory panels taste samples to ensure the flavor matches the established profile. On top of that, microbiological testing verifies that no harmful organisms are present, and shelf life trials confirm that the product will remain stable through its intended storage period. The machinery in a Red Bull plant is highly automated, reducing human contact with the product to a minimum. Operators oversee systems via control rooms equipped with touchscreens that display real-time data on mixing temperatures, carbonation levels, filler speeds, and line efficiency. Maintenance crews work behind the scenes to keep pumps, compressors, and conveyors in top condition, as any downtime on a high-speed beverage line can be costly. Sustainability is also a growing focus in Red Bull production. Aluminum cans are already among the most recyclable packaging formats, and many plants source cans with a high percentage of recycled content. Water purification systems are designed to minimize waste, and heat recovery from pasteurization can be used to preheat water for syrup preparation. Efficient compressors and motors reduce energy consumption, and many facilities work to optimize transport logistics to cut fuel use in distribution. What makes the Red Bull process particularly interesting is how tightly controlled and repeatable it must be. The drink's formula is identical worldwide, which means a can produced in Austria should taste exactly the same as one produced in the United States or Asia. Achieving this level of uniformity across multiple plants requires not only identical recipes and ingredients, but also standardized equipment, operating procedures, and quality control protocols. Every plant is essentially a mirror of the others, ensuring that no matter where it's made, Red Bull delivers the same signature flavor, carbonation, and energizing effect. Every can of Monster begins with its ingredients, and the largest component is water. The water used in Monster Energy production is not simply drawn from a tap, it is subjected to a thorough purification process to remove any dissolved solids, organic compounds, or microorganisms that could affect taste, appearance, or stability. The typical sequence starts with coarse filtration to catch sediment, followed by activated carbon filters to strip out chlorine and odors. Reverse osmosis membranes then reduce mineral content to near zero, creating a blank canvas for the flavor formulation. As a final step, ultraviolet light or ozone is used to sterilize the water before it enters the mixing tanks. Next come the sweeteners, functional additives, acids, and flavors that give Monster its distinctive taste and energy-boosting profile. Cane sugar or beet sugar may be used along with glucose or high fructose corn syrup, depending on the variant and market. These sugars arrive in bulk either as crystalline solids or liquid syrup in tanker trucks. Functional ingredients include caffeine for stimulation, taurine as an amino acid additive, and B vitamins like niacin, riboflavin, vitamin B6, and vitamin B12 to support energy metabolism. Some varieties incorporate plant extracts such as ginseng or guarana, which add both flavor and functional appeal. Acids like citric and sometimes malic acid adjust the pH for tanginess and preservation, while natural and artificial flavors create the unique profile for each Monster variety, from the classic green logo flavor to tropical, coffee-based, and sugar-free blends. The first main step in production is the preparation of the concentrate or syrup. In large stainless steel mixing vessels, sugar is dissolved into heated purified water under gentle agitation. If liquid sweeteners are used, they are pumped directly in and blended. Functional powders like caffeine and taurine are carefully weighed and added in controlled sequences to ensure complete dissolution without clumping. B vitamins, which are sensitive to heat, are typically added later in the process to preserve potency. The plant extracts, if used, are measured and incorporated at specific points, often emulsified, to ensure they disperse evenly throughout the drink. Flavor concentrates, which can be highly potent, are metered into the mix using precision dosing pumps. These concentrates often contain a mixture of flavor oils, sweeteners, and acids in a stable base that integrates easily into the water-sugar matrix. Because Monster produces a wide variety of flavors, the plant must be capable of switching from one concentrate to another with minimal downtime. A challenge that requires clean-in-place systems to flush and sanitize mixing tanks and pipelines between batches. Once the syrup is fully blended, it is tested in the quality control lab for sweetness, acidity, caffeine content, and flavor profile. The lab team uses sensory analysis alongside instrumental testing to ensure the mixture matches the established standard. Only when it passes these checks is it moved forward. The next stage is dilution and carbonation. The concentrated syrup is blended with additional purified water in large batch tanks to reach the target formulation for the finished drink. This diluted beverage is chilled to near freezing temperatures to maximize the solubility of carbon dioxide during carbonation. The chilled liquid enters a carbonator, where CO2 is injected under high pressure and mixed through fine diffusers or inline mixers. The carbonation level is closely controlled. Too little, and the drink will taste flat. Too much, and it will foam excessively during filling. Once carbonated, the beverage moves immediately to the filling lines. Monster Energy is almost always packaged in aluminum cans, chosen for their lightweight, barrier properties, and recyclability. These cans arrive at the plant in massive pallets of unfilled containers, often printed with Monster's signature claw mark logo and variant-specific graphics. Before filling, each can is inverted and passed through a rinser, which uses either deionized water or ionized air to remove any dust or particles. The cans travel into high-speed rotary filling machines, where they are filled from the bottom up to reduce foaming and preserve carbonation. Each filler head dispenses an exact volume, ensuring every can meets legal net content on my requirements. Immediately after filling, the cans pass into a seaming machine, where an aluminum lid is placed on top and mechanically rolled into place to form a double seam that locks the contents in airtight. This seaming process is a critical control point. Improperly sealed cans can lose carbonation or leak, so seamer performance is constantly monitored. Sealed cans are inverted briefly so that the liquid inside can contact the underside of the lid, which acts as a quick sterilization step. Depending on the plant's process, the cans may then undergo tunnel pasteurization. Moving through a heated water spray tunnel that raises the beverage temperature for a specific time to kill any microorganisms. Or may rely on aseptic filling techniques that eliminate the need for heat treatment. Once pasteurized or otherwise stabilized, the cans are cooled rapidly to prevent heat damage to vitamins and flavors. They then pass through a series of inspection systems. Automated vision cameras check for dents, damaged seams, or incorrect graphics. Check weighers ensure that each can contains the correct amount of product, and any deviation triggers an automatic rejection. Many lines also incorporate inline gas analysis to confirm carbonation levels in the finished product. The approved cans move into the secondary packaging area, where they are grouped into multi-packs. This may involve cardboard carriers, shrink-wrapped bundles, or trays depending on the market. Automated packers arrange the cans in the correct pattern, wrap or enclose them, and send them toward the case packing stage. Here, multi-packs are loaded into corrugated shipping cartons, which are sealed, coated with batch and date information, and stacked by robotic palletizers. Pallets are wrapped in stretch film to secure the load and sent to the warehouse for storage. Even though Monster Energy is shelf-stable at room temperature, it is generally stored in cool, dry conditions to maintain flavor and carbonation quality. From the warehouse, products move through distribution networks to retail shelves worldwide. Behind all of these steps is a rigorous quality control program. The production team pulls samples at every stage: syrup preparation, dilution, carbonation, filling, and post-packaging to confirm compliance with product specifications. Analytical labs test for caffeine content, sugar level, vitamin potency, pH, and carbonation. Microbiological testing ensures that no spoilage organisms are present. Sensory panels evaluate taste, aroma, and mouthfeel to maintain brand consistency. The machinery that makes this possible is heavily automated. Operators work from control panels in climate-controlled rooms, monitoring temperatures, pressures, flow rates, and carbonation levels via touchscreen interfaces. Programmable logic controllers coordinate the entire process, from mixing through palletizing, and sensors throughout the plant send real-time feedback. This automation allows Monster to produce enormous volumes with minimal downtime, while meeting strict safety and quality standards. Sustainability considerations are increasingly built into Monster's operations. Aluminum cans are highly recyclable, and many suppliers provide them with a significant proportion of recycled content. Water purification systems are designed to recover and reuse as much water as possible in non-product applications like cooling or cleaning. Heat from pasteurization is often recovered and used to preheat water for syrup preparation, reducing energy demand. Transportation logistics are optimized to reduce emissions, and some plants have moved towards renewable energy sources for part of their power. What is most striking about Monster Energy production is its consistency. The brand's image may be chaotic and wild, but the drink inside is the product of careful, repeatable processes that leave nothing to chance. Every step is measured, every variable tracked, every can inspected, ensuring that when a consumer pops the tab and hears that sharp hiss of carbonation, they get exactly the flavor, mouthfeel, and energy hit they expect, whether they bought it in a gas station in California or a convenience store in Seoul. The making of a can of Celsius Energy is a study in a modern beverage manufacturing where health-focused marketing meets industrial-scale precision. Although the drink is promoted as a fitness or metabolism-boosting energy beverage, the underlying production process is much like that of other carbonated functional drinks. A carefully balanced formula of water, sweeteners, active ingredients, and flavors blended, carbonated, and packaged under conditions designed to maintain purity, consistency, and shelf stability across millions of units. It begins with the most abundant ingredient, water. Water quality is paramount in Celsius production because any dissolved minerals, organic matter, or off flavors could interfere with the delicate flavor balance and the stability of the added functional ingredients. Purification is achieved through a series of treatments. First, the incoming water is screened through coarse filters to remove particles. Activated carbon filters then strip out chlorine, residual odors, and organic compounds. Reverse osmosis membranes reduce dissolved solids to extremely low levels, creating a neutral base. Finally, ultraviolet light or ozonation is applied to sterilize the water before it enters the formulation tanks. Once the water supply is ready, the functional and flavor ingredients that distinguish Celsius are prepared. Unlike traditional energy drinks that lean heavily on sugar and caffeine alone, Celsius incorporates a blend of caffeine from both synthetic and natural sources, such as green tea extract and guarana seed extract. It also features taurine, B vitamins, vitamin C, and in many varieties, additional plant extracts such as ginger root extract for a warming, metabolism-supporting effect. Some variants are sweetened with cane sugar, while many zero sugar options use non-nutritive sweeteners like sucralose or stevia extract. Acids like citric acid and malic acid are used to balance the flavor profile and help preserve freshness, while natural flavors, often fruit-based, create the distinct taste of each variety, from sparkling orange to peach vibe. The first major step in production is creating the base concentrate or syrup. This happens in large stainless steel mixing vessels equipped with high shear agitators or propeller mixers to ensure complete dispersion of both solids and liquids. For sugar-containing variants, crystalline sugar is metered into the purified water and dissolved at a controlled temperature to speed up the process without causing caramelization. If the formula calls for 0-calorie sweeteners, these are introduced in microgram precise quantities via automated dosing systems, as their sweetness intensity is many times greater than that of sugar. Functional powders such as caffeine, taurine, and vitamin C are weighed with laboratory-grade scales before being added. Plant extracts often arrive as liquid concentrates or fine powders and may require pre-dissolution in a small amount of water or glycerin to ensure they blend smoothly without clumping. For heat-sensitive ingredients like vitamin C, addition occurs towards the end of mixing to minimize degradation. Throughout this stage, the pH is monitored and adjusted as needed, since certain active compounds are more stable within specific acidity ranges. Once all solids are dissolved and liquids are homogenized, flavoring compounds are introduced. These may be natural fruit essences, essential oils, or compounded flavors from specialist suppliers. The flavoring process is highly sensitive. Even slight, over, or underdosing can shift the sensory profile away from the established standard. The completed syrup is sampled and sent to the in-house quality control laboratory for analysis. There, technicians measure sugar concentration, acidity, caffeine content, and other activities, and conduct sensory evaluations to confirm taste matches the reference profile. After passing these checks, the syrup is diluted with more purified water to the final formulation strength in large batch tanks. At this stage, the beverage is chilled to near freezing temperatures in preparation for carbonation. Carbonation is one of the signature sensory features of Celsius's sparkling varieties, and it is carried out with precise control over dissolved CO2 content. The chilled liquid flows into a carbonation unit where carbon dioxide gas is injected under pressure, dissolving evenly into the liquid. The goal is to achieve a crisp, sparkling mouthfeel without excessive foam that could cause filling issues. From the carbonator, the beverage is pumped directly to the filling lines. Celsius is typically packaged in slim aluminum cans, often the 12-ounce or 355 milliliter size, chosen for their portability, shelf life stability, and recyclability. The empty cans arrive at the plant in palletized stacks and are fed onto conveyors. Before filling, they undergo a rinse using ionized air or deionized water to remove any dust or particles. The cleaned cans are inverted, then righted, and sent into the filling carousel. The filling process operates at high speed, often hundreds of cans per minute, and is done under conditions that protect carbonation. Each filler head dispenses an exact volume from the bottom up to reduce turbulence. Immediately after filling, the cans move into a seaming machine, where an aluminum lid is placed on each and mechanically crimped to form an airtight seal. This seam is a critical element of the can's integrity, and seaming stations are regularly checked with seam micrometers to verify proper formation. Sealed cans may pass through a pasteurization tunnel, depending on the plant's preferred stability method. In pasteurization, the cans travel along a conveyor under sprays of hot water that raise the internal beverage temperature to a specific target for a defined time, killing any potential microorganisms. Afterward, the cans are cooled quickly to protect heat-sensitive nutrients. In some plants, aseptic filling technology is used instead, allowing the drink to be filled into sterilized cans without the need for post-fill heat treatment, which can better preserve delicate flavors and vitamins. Once cooled, the cans pass through a series of inspection systems. Vision systems scan for dents, label defects, or improper graphics. Checkweighers ensure the net content is correct, and any can outside the tolerance is automatically rejected. Inline gas analyzers may measure CO2 content to confirm carbonation consistency. Approved cans enter the secondary packaging stage, where they are grouped into multi-can packs. Cardboard sleeves, shrink film, or tray packs are applied depending on the distribution plan. Multi-packs are collated into corrugated shipping cases, which are sealed with glue or tape and printed with batch codes for traceability. Robotic palletizers stack these cases onto pallets in stable patterns, after which the pallets are wrapped in stretch film to secure them for transport. The finished pallets move into climate-controlled warehouse storage. Celsius products are shelf-stable, but temperature control helps maintain flavor, carbonation, and nutrient stability over the shelf life. From here, pallets are shipped to distributors, retailers, and online fulfillment centers worldwide. Throughout this process, quality control is constant. Samples from each batch are tested for caffeine level, vitamin potency, flavor accuracy, pH, and carbonation before release. Microbiological tests ensure no spoilage organisms are present. Sensory panels evaluate the finished drink for mouthfeel, aftertaste, and aroma, comparing it to the brand standard. Because Celsius positions itself in the better-for-you beverage category, consistency in active ingredient content is especially critical, and certificates of analysis often accompany each production run. Behind the scenes, this is all enabled by a network of highly automated equipment controlled by programmable logic controllers. Operators monitor the process from control stations, adjusting parameters like mixing speed, carbonation pressure, or filler settings as needed. The plant's clean-in-place systems allow tanks, pipelines, and fillers to be washed and sanitized automatically between batches, ensuring hygiene without extended downtime. Sustainability is an increasing focus in Celsius production. Aluminum cans are infinitely recyclable, and many suppliers now provide cans with a high percentage of recycled content. Plants work to reduce water use in cleaning and cooling, recover heat from pasteurization to preheat processed water, and optimize transport routes to cut emissions. Some facilities integrate renewable energy into their operations, such as solar panels or purchase agreements for green electricity. What makes the Celsius production process interesting is the careful balance between functional beverage science and mass-market beverage engineering. While the plant extracts and nutrient additions require precise handling to maintain potency and stability, the large-scale manufacturing environment demands speed and efficiency. The result is a beverage that can deliver consistent taste, carbonation, and nutritional content across millions of cans, while supporting the brand's positioning as a lifestyle-oriented, health-conscious energy drink. It all begins with the chicken itself, fresh, never frozen, and selected according to strict specifications that have been standardized over decades. At the heart of KFC's fried chicken production is consistency, and that starts with sourcing poultry from highly regulated farms, often contracted directly to supply birds that meet stringent criteria for weight, size, age, and health. These chickens are typically raised under controlled conditions, with monitored feeding schedules and veterinary oversight, ensuring uniformity in muscle development and fat content. Farmers work closely with the suppliers to deliver birds that fall within the optimal range for processing, which generally hovers around 4 to 6 pounds per whole bird, depending on the regional market. Once the birds arrive at the poultry processing plant, they undergo a sequence of highly regulated steps designed to transform them into the individual cuts used in KFC's iconic fried chicken buckets. The first step is stunning and slaughter, where automated systems humanely render the birds unconscious before they are swiftly slaughtered. This is followed by scalding, immersing the carcasses in warm water to loosen feathers, and defeathering using a mechanical plucking system that employs rotating rubber fingers to strip feathers from the skin without damaging the flesh. The next phase involves evisceration, where internal organs are removed through a series of automated mechanical arms and cutting systems. Inspectors, both human and digital, examine the internal cavities for any signs of disease or contamination. The birds are then washed thoroughly in a series of chilled water baths and antimicrobial sprays to reduce surface bacteria. After this, the carcasses are chilled rapidly, often through immersion in ice water or air chilling tunnels, to bring the internal temperature down to safe levels before further processing. With the whole birds chilled and inspected, they are transferred to the cutting line. This is where the chicken is portioned into the familiar cuts used in KFC recipes: drumsticks, thighs, breasts, wings, and occasionally rib portions, depending on the market. High-speed blades and vision-guided robotic systems ensure that each piece is cut uniformly. Some facilities even use X-ray and laser-guided cutting to detect bone structure and fat lines, optimizing yield and reducing waste. The chicken pieces are then sorted by size and weight, ensuring every batch has a consistent mix for packaging and preparation. After cutting, the chicken is placed into sanitized plastic totes or stainless steel trays and sent to the marination area. This is a crucial step that lays the foundation for KFC's signature flavor. The original recipe chicken is soaked in a wet brine that typically includes water, salt, and phosphate-based tenderizers to enhance juiciness and flavor retention. The chicken is placed into large tumblers, rotating drums with paddles inside that gently agitate the meat to ensure thorough penetration of the brine. This marination process typically lasts for a fixed duration, anywhere from 30 minutes to several hours, depending on the specific product line. But marination is just the beginning. What truly sets KFC apart is the breading process, a meticulously controlled step where secrecy and technique intertwine. The chicken is removed from the brine and allowed to drain slightly before being transferred to the breading stations. The breading mixture, known for its secret blend of 11 herbs and spices, is kept under strict control. At the manufacturing level, this seasoning is produced in centralized spice blending facilities, measured with pharmaceutical-level precision, and shipped to stores or distribution centers in tamper-proof bags. Operators follow a carefully choreographed breading procedure known as the 7-to-10-7 method. First, the The chicken is placed into a flat metal pan with the dry breading mix and hand-tossed 7 times in a specific pattern to ensure an even coating. Then the pieces are compressed down into the breading mixture for 10 seconds. This step helps the coating adhere and creates the famous textured crust. Finally, the pieces are shaken 7 more times and arranged neatly onto perforated trays for the next stage. This manual method, despite being labor-intensive, is a cornerstone of KFC's identity and helps achieve the distinctive craggy exterior that customers recognize instantly. Once breaded, the chicken is moved to the fryers. KFC uses high-capacity pressure fryers, commercial machines that resemble deep fryers, but with tightly sealed lids that allow cooking under pressure. This equipment is critical for achieving the brand's signature texture, crispy on the outside, juicy on the inside. The sealed environment traps steam from the chicken's internal moisture, cooking it rapidly while locking in juices. The breaded pieces are loaded into metal baskets, which are then placed into the preheated pressure fryers filled with proprietary frying oil blends, typically high in stability and low in trans fats. Each fryer is pre-programmed to precise cooking parameters, controlling temperature and time based on the chicken type: bone-in, boneless, tenders, or wings. For original recipe bone-in chicken, the typical cooking cycle runs around 10 to 15 minutes at roughly 325 degrees under pressure. As the pressure builds, the internal temperature of the chicken rises quickly, reducing cook time while preserving moisture. Throughout the cooking process, sensors inside the fryer monitor oil temperature, pressure levels, and cooking duration, ensuring every batch turns out uniform and safe to eat. Once cooking is complete, the fry baskets are lifted automatically or by hand, and the chicken is allowed to drain for a brief period over the oil vat. Operators then transfer the finished product to a holding station, typically a heated cabinet or a moisture-controlled drawer that maintains the chicken at a safe temperature, usually above 140 degrees F, while preventing the crust from getting soggy. These holding cabinets are set to timers that ensure chicken is only kept for a limited time before it is discarded or rotated out, reinforcing KFC's strict freshness policy. Throughout this entire process, food safety is paramount. Every station is equipped with hand-washing sinks, sanitizer dispensers, and cleaning schedules that are enforced hourly. Employees wear gloves, aprons, and hairnets or caps, and facilities conduct routine microbial testing on surfaces and air to minimize contamination risks. Temperature logs, batch records, and fryer oil quality checks are performed regularly. The oil itself is filtered several times per day using built-in filtration systems that remove particulates and extend the oil's usable life while maintaining flavor quality. But the process doesn't begin or end in the kitchen. At the supply chain level, KFC relies on a cold chain network that keeps the chicken and ingredients at safe temperatures from the processing plant to the store. After the chicken is marinated and portioned at regional facilities, it is vacuum sealed or packed into airtight food-grade plastic bags, then stored in refrigerated trucks with active temperature tracking systems. GPS-enabled trailers ensure the logistics team can monitor both temperature and location in real time, avoiding spoilage or delays. The spice blends, breading flour, oil blends, and packaging materials are all shipped through similarly optimized networks, allowing stores to receive fresh inventory on a scheduled basis without interruption. When the chicken finally reaches the individual KFC restaurants, it is stored in walk-in coolers, prepped according to the exact procedures laid out by corporate training, and cooked fresh on-site throughout the day in small batches to keep up with demand. The entire system is designed for scalability and control. From a small store in a rural town to a flagship location in a major metropolis, the chicken tastes almost identical. That's the power of systematized food production at scale. Interestingly, much of KFC's fried chicken production still retains a manual, human-guided feel despite the high-tech systems that support it. While robotics and automation are increasingly common in many fast food chains, KFC's breading process continues to rely heavily on trained workers. This combination of human skill and industrial precision contributes to the unique texture and flavor of the final product. It all begins with the raw materials. At the core of the Big Mac are its two beef patties, 100% pure ground beef, with no fillers, additives, or preservatives. These patties are made from specially selected cuts of beef, typically chuck, round, and sirloin, all blended to achieve McDonald's-specific fat-to-lean ratio, usually around 80-20. The cattle are sourced from approved ranches and farms, where animal welfare, feed quality, and traceability are tightly controlled. These suppliers operate under strict auditing and food safety programs to ensure consistency and safety throughout the entire supply chain. At the beef processing plants, the meat is first received in chilled form and stored in temperature-controlled environments. It then moves to large-scale grinders where the cuts are ground to a uniform consistency. The grinding process uses precision-engineered machinery that not only ensures even texture, but also mixes the fat content evenly throughout the meat. After grinding, the meat is portioned into exact patty sizes using high-speed forming equipment. Each Big Mac patty is a 1.6 ounce round that measures precisely to fit the 3-part sesame seed bun. Once the patties are formed, they are immediately flash frozen using cryogenic tunnels or spiral freezers. This locks in moisture and prevents microbial growth while maintaining the structural integrity of the patty. The frozen patties are then stacked into cartons, sealed, and loaded into refrigerated trucks that maintain a cold chain at all times. They are shipped to McDonald's distribution centers, which in turn supply local restaurants with scheduled deliveries to ensure freshness and efficient inventory management. But a Big Mac isn't just beef. Another critical component is the famous 3-part sesame seed bun: the crown, the club, and the heel. These buns are produced in large-scale commercial bakeries that specialize in McDonald's specifications. The dough is made from wheat flour, water, yeast, sugar, and conditioners to ensure softness and volume. The mixing and proofing process is closely monitored by computerized systems that control dough temperature and humidity. Once proofed, the dough is portioned into perfectly sized balls and dropped into custom baking molds designed specifically for the Big Mac's 3-part structure. The top bun is topped with sesame seeds just before baking. Conveyor ovens bake the buns at precisely calibrated temperatures for consistent color, texture, and internal moisture. After baking, buns are cooled on spiral cooling racks, then sliced, and the 3 segments are separated and packaged accordingly. Like the patties, the buns are then flash frozen or refrigerated and shipped to McDonald's outlets. Another defining component of the Big Mac is its sauces and toppings, specifically the Big Mac Special Sauce. The exact formula is proprietary, but the flavor is unmistakable. A tangy, creamy, slightly sweet sauce that combines elements of mayonnaise, mustard, relish, garlic, onion powder, and other spices. This sauce is manufactured in centralized condiment processing facilities, where ingredients are blended in large stainless steel tanks using industrial mixers that maintain a homogeneous emulsion. The final product is pumped into sealed, portion-controlled containers that are shipped cold to restaurants. In addition to the sauce, there are sliced pickles, dehydrated onions that are rehydrated on-site, shredded iceberg lettuce, and American cheese. The pickles are cut from whole cucumbers and brined in tanks with a proprietary vinegar and spice solution. They're sliced to a uniform thickness, then packed in brine to retain crunch and flavor. The onions come pre-chopped and dehydrated to extend shelf life and reduce spoilage. They are soaked in cold water at the store level before use. Lettuce is shredded in controlled processing plants and packed into vacuum-sealed bags. It must meet specific dimensions for length and width to ensure even coverage and manageable volume in the sandwich. The cheese, a processed slice tailored for meltability and flavor stability, is individually wrapped and delivered refrigerated. At the restaurant level, the Big Mac is assembled in a precise, time-tested sequence designed for speed and uniformity. When a customer places an order, the kitchen system relays it to the grill and assembly line. The patties are cooked on a dual-sided clamshell grill, a piece of kitchen equipment that cooks both sides of the patty simultaneously. This reduces cook time to less than a minute, while ensuring the internal temperature reaches the USDA required safe zone of 155 degrees Fahrenheit or higher. The grills are calibrated multiple times a day to maintain consistent heat, and they include timers and temperature sensors that alert the crew when patties are done. Simultaneously, the buns are toasted on a vertical conveyor toaster that crisps the inside surfaces while leaving the exterior soft. Each bun, top, middle, and bottom, is inserted into a specific slot in the toaster, ensuring that they emerge in the correct sequence for stacking. The bun toaster is also calibrated for toast color and surface temperature, both of which affect the texture and structural integrity of the final sandwich. Once the patties and buns are ready, the assembly begins on a stainless steel prep table or station called the sandwich build line. Each component is added in exact order. The heel receives a half teaspoon of rehydrated onions, followed by shredded lettuce, 1 slice of cheese, and the first cooked beef patty. The middle bun is then placed on top, followed by a second layer of sauce, onions, lettuce, and pickles, then the second patty. Finally, the top bun is placed to crown the entire structure. Employees are trained to assemble the Big Mac with a high degree of consistency, using scoops and dispensers designed to deliver precise amounts of sauce, lettuce, and onions. Visual guides are often posted above the station, and training involves repetition to internalize the build order and portion sizes. Speed is crucial, but accuracy takes priority. Each Big Mac must be indistinguishable from the next. Once assembled, the sandwich is wrapped in specially designed cardboard clamshells or wrappers that help maintain heat without causing sogginess. These are placed in warming areas or immediately bagged for customer pickup, depending on the workflow of the kitchen. Each Big Mac is usually served within a 5 to 10 minute window of cooking, ensuring it is hot, fresh, and true to form. Food safety and quality assurance are embedded in every stage of this process. The patties are temperature checked with digital thermometers. Sauce containers are labeled with use by times. Lettuce and onions are discarded after a certain number of hours out of refrigeration. Crew members follow strict hygiene protocols, including hand washing every hour, wearing gloves, and rotating utensils to prevent cross-contamination. Regular audits and surprise inspections ensure compliance with these standards. McDonald's kitchens also operate with a high level of automation and integration. Point-of-sale systems are linked to kitchen monitors, which display order sequences in real time. Inventory systems track ingredient usage and automatically flag restocking needs. Even the toaster and grill equipment is connected to central management systems that log performance data, usage cycles, and maintenance schedules. Behind the scenes, logistics play a crucial role in Big Mac production. From farm to fryer, the ingredients move through a vast cold chain network supported by regional distribution centers. These hubs maintain constant temperature control and manage stock rotation to ensure that every restaurant has fresh, usable inventory. McDonald's works closely with third-party logistics companies and in-house supply teams to coordinate deliveries across thousands of outlets every day. Even sustainability is being integrated into the Big Mac's life cycle. McDonald's has committed to sourcing beef more responsibly, using packaging materials that are recyclable or compostable, and reducing waste in the supply chain. Many of the buns are baked in facilities that run on renewable energy, and fryers now use low-emission heating systems. The lettuce and pickles are sourced from farms that practice water conservation and integrated pest management. In the end, the Big Mac is more than a sandwich. It's a manifestation of precision food engineering on a global scale. What might seem like a simple fast food item is the result of decades of refinement in agriculture, logistics, processing, and food safety. The carefully orchestrated choreography of farmers, food scientists, line cooks, and engineers ensures that every customer experiences the same taste, texture, and satisfaction with every bite. Whether it's the sizzle of the patties on the grill or the final crown of the sesame bun, every step is designed to deliver that unmistakable Big Mac experience. It all starts with the dough. Domino's dough is made in regional commissaries, large-scale production facilities that supply fresh dough to stores several times a week. These commissaries receive shipments of high-quality wheat flour from trusted grain suppliers. The flour, typically enriched and with a mid-range protein content around 12%, is combined with water, yeast, salt, sugar, and a small amount of oil in massive stainless steel mixers. These mixers, with capacities ranging from hundreds to thousands of pounds, mix the dough until it reaches the desired elasticity and gluten development. The dough is then allowed to rest and rise in temperature and humidity-controlled proofing rooms. These chambers regulate fermentation precisely, letting the yeast activate and produce carbon dioxide, which is what gives the dough its airy structure. This stage is not rushed. Domino's prioritizes flavor and texture, allowing the dough to ferment for several hours or even overnight to develop deeper taste and a balanced chew. After proofing, the dough is portioned into individual balls using industrial dough dividers and rounders. Each ball is scaled for the correct pizza size: small, medium, large, or extra large, and placed into trays lightly coated with cornmeal or oil to prevent sticking. These trays are stacked into rolling racks and moved into refrigerated holding rooms. Chilled to slow further fermentation, the dough balls are now ready for transport. They're boxed, loaded into cold chain delivery trucks, and shipped to Domino's outlets across the region on a tightly managed delivery schedule. Now comes the tomato sauce, an essential component that gives every pepperoni pizza its acidic punch and signature flavor base. The sauce is made at centralized processing plants using vine-ripened tomatoes, typically harvested at peak season and steam-peeled for optimal flavor preservation. The tomatoes are ground and mixed with a proprietary blend of spices, including oregano, basil, garlic powder, onion powder, salt, and sometimes a pinch of sugar to balance acidity. This sauce is then pasteurized to ensure shelf stability and safety, and filled into sealed plastic pouches or buckets, which are shipped refrigerated to each Domino's location. Cheese, too, is a cornerstone ingredient in every pepperoni pizza. Domino's uses a special low-moisture, part-skim mozzarella blend developed for optimal melt, stretch, and browning. Large cheese manufacturing plants shred or dice the mozzarella into uniform pieces that fall easily onto the pizza and melt consistently. The cheese is bagged, nitrogen flushed to prevent spoilage, and stored cold until it's needed. Domino's has strict cheese specifications that regulate fat content, meltability, and even browning color curves during baking. And of course, there's the pepperoni. Domino's pepperoni is a type of cured, spiced sausage made from a mix of beef and pork. The meat is ground and blended with a spice mixture that includes paprika, garlic, crushed red pepper, fennel seed, and curing salts. After being emulsified, the mixture is stuffed into collagen casings and fermented to develop its tangy flavor profile. The pepperoni is then slow-dried, sometimes smoked, and aged until it reaches the correct firmness. Once matured, it's sliced into perfect, thin rounds that crisp slightly when baked but retain their juicy center. These slices are packed into refrigerated cases, typically with a layer of wax paper to prevent sticking, and distributed to stores for daily use. At the store level, the pizza making process begins when an order is received, either online, via app, or in-store. The store crew retrieves a dough ball from the walk-in cooler and places it on a prep table dusted with cornmeal or flour. Unlike hand-tossed pizzerias, Domino's uses a combination of manual and mechanical techniques to stretch dough. The dough ball is pressed using a dough press or roller to achieve the correct size and thickness. Then it may be hand-finished to achieve an even round shape with a defined edge, or cornicione. Once the crust is prepared, the pizza moves down the make line. A ladle of tomato sauce is spread in a spiral motion from the center outward, leaving a consistent border around the edge. Precision here is key. Too much sauce and the crust gets soggy. Too little and the pizza lacks flavor. Domino's uses portion-controlled utensils to ensure uniform application across thousands of pizzas a day. Next comes the cheese. Employees grab pre-measured amounts of shredded mozzarella from cold bins and scatter it evenly over the sauced crust, making sure to reach the edges to maximize melt and appearance. The cheese-to-sauce ratio is carefully designed to complement the crust thickness and baking conditions in the oven. Domino's often uses cheese guides or weight scales to prevent under or over application. Then it's time for the pepperoni, the star of the show. Domino's applies pepperoni in a uniform pattern, usually a ring-based layout that ensures each slice of the final pizza gets equal coverage. The pepperoni is placed on top of the cheese so it crisps and curls slightly during baking, creating those little greasy, flavorful cups that have become a hallmark of American pepperoni pizza. The number of pepperoni slices is not left to chance. Domino's has precise count targets per size, such as 30 slices for a medium and 40 for a large, ensuring every customer receives the expected experience. Once built, the raw pizza is placed onto a pizza screen or baking tray and sent into a conveyor oven. Domino's signature baking method. These ovens, called impinger ovens, are long, tunnel-like machines that use jets of superheated air to cook the pizza quickly and evenly. The oven belt moves at a fixed speed, typically cooking a pizza in about 6 to 7 minutes at a temperature of approximately 465 degrees Celsius to 500 degrees. The impingement cooking method forces hot air onto the top and bottom surfaces of the pizza simultaneously, ensuring a crisp crust and melted, browned cheese with consistent results. As the pizza exits the oven, crew members perform a quick visual check for doneness. The cheese should be fully melted and bubbling, the pepperoni slightly curled with crispy edges, and the crust golden brown. The baked pizza is transferred to a cutting board and sliced with a rolling blade into even segments, typically 8 for a large pizza. The blade is wiped between uses to prevent sauce and cheese buildup. The pizza is then placed into a specially designed Domino's pizza box made from recycled corrugated cardboard. These boxes are ventilated to allow excess steam to escape, preventing sogginess during delivery. Each box is folded and branded with Domino's blue and red logo and has space for order stickers, promotional labels, and QR codes. A thermal lining or pizza insert may also be used in some regions to help retain heat during transport. Once boxed, the pizza is either handed over to a customer in-store or placed into an insulated delivery bag. These bags are engineered to retain heat and allow limited airflow, keeping the pizza hot but not steamy. Domino's delivery drivers follow optimized GPS routes generated by proprietary software that prioritizes speed and traffic conditions. Many stores use heat racks or warming stations to hold pizzas briefly while waiting for drivers or curbside pickup. Behind the scenes, Domino's uses sophisticated technology to monitor every step. The point-of-sale system automatically tracks inventory levels. Real-time analytics inform store managers about the number of pizzas being ordered, the time each step takes, and potential bottlenecks. Domino's Pizza Tracker gives customers live updates on the progress of their order, from prep to baking to out for delivery, driven by timestamps and kitchen inputs. Cleanliness and food safety are integral to every stage. Dough trays and utensils are washed in commercial dish machines between uses. Gloves are worn and changed frequently. Prep stations are sanitized regularly throughout the day. All cold ingredients are stored in reach-in coolers with thermometers to maintain optimal temperature. Internal audits and third-party inspections ensure compliance with food safety standards and corporate procedures. Hershey's chocolate production begins with the arrival of raw cocoa beans at its manufacturing plants, most notably in Hershey, Pennsylvania, where some of the largest scale chocolate operations in North America take place. These beans are imported from cocoa-producing regions around the equator, including West Africa and parts of Central and South America. Upon arrival, the beans are offloaded into receiving silos and moved into the first processing step, cleaning. Powerful vibrating screens, aspirators, and magnetic separators remove debris, stones, twigs, dust, and any metallic fragments that may have entered the shipment during transit. Following cleaning, the cocoa beans are fed into Hershey's proprietary roasting system. The roasting process is designed not just to sterilize the beans, but to precisely control flavor development. The machines are capable of adjusting roast temperature, humidity, and dwell time based on the origin, size, and moisture content of each batch. Beans are typically roasted at temperatures ranging from 120 to 160 degrees Celsius. This is where the characteristic chocolate aroma begins to develop, as volatile compounds are released and the Maillard reaction activates, producing hundreds of unique flavor notes that define Hershey's mild, sweet chocolate style. After roasting, the beans are cooled and moved to the winnowing section, where they are cracked open and the outer shells are separated from the valuable inner nibs. Winnowing is accomplished using a combination of mechanical cracking and airflow separation. The shells, now removed, are often collected and repurposed as agricultural mulch or biomass fuel. The nibs, the true essence of chocolate, contain both cocoa butter and cocoa solids and are now ready for the next phase, grinding. The nibs are fed into high-capacity industrial grinding mills, where intense mechanical shear forces break down the cellular structure and release the natural cocoa butter, forming a dense, fluid paste known as chocolate liquor. Despite its name, chocolate liquor contains no alcohol. This liquor is a pure, unsweetened, dark brown substance composed entirely of finely ground cocoa particles suspended in cocoa butter. From here, the liquor may go into temporary holding tanks or be immediately sent to blending tanks, depending on product demand. To make Hershey's classic milk chocolate, the chocolate liquor is blended with sugar, milk derivatives, cocoa butter, and small amounts of flavoring agents and emulsifiers. What makes Hershey's process unique is its use of fresh milk, originally pioneered by Milton Hershey himself, which is condensed and cooked on site. This milk is blended with sugar and chocolate liquor to form a slurry, which is then dried into what's known as milk crumb. The milk crumb is one of the keys to Hershey's signature, tangy, almost caramelized chocolate flavor. Unlike many European chocolate makers who use dry milk powders, Hershey's milk crumb production adds distinctive cooked dairy notes that have become synonymous with the brand's taste. The crumb mixture is then blended with additional chocolate liquor and cocoa butter in massive mixers to create a semi-fluid chocolate paste. This paste now contains all of the major components of Hershey's chocolate: milk solids, sugar, cocoa mass, and cocoa butter. However, it still needs to be refined to achieve the ultra-smooth texture that consumers expect. This refinement is achieved using a 5-roll mill, a piece of precision equipment where the chocolate paste is passed through a series of steel rollers that reduce particle size down to around 15 to 20 microns, small enough that the human tongue can no longer detect individual sugar or cocoa particles. Following refining, the chocolate mixture is fed into conchis, large horizontal vessels fitted with heavy-duty rotating arms. Conching is both a mechanical and thermal process in which chocolate is kneaded and aerated for several hours at controlled temperatures. During this stage, volatile acids are evaporated, off flavors are reduced, and cocoa solids become fully coated in cocoa butter, resulting in a more uniform flavor and mouthfeel. Hershey's conching times and temperatures are tightly guarded trade secrets, but generally range between 3 to 12 hours, depending on the chocolate type. Once conching is complete, emulsifiers like soy lecithin or PGPR may be added to improve flow characteristics and ensure the chocolate performs consistently during molding and enrobing. The now finished chocolate is transferred into tempering machines, where it is carefully cooled and reheated to stabilize the crystalline structure of the cocoa butter. Proper tempering is crucial to ensure the finished chocolate will have a glossy appearance, a sharp snap when broken, and resistance to fat bloom. Tempered chocolate is then routed to forming lines. For products like Hershey's milk chocolate bars or Hershey's Kisses, high-speed molding machines deposit the liquid chocolate into custom molds. These molds are vibrated to eliminate air bubbles and achieve uniform density before passing through long cooling tunnels. As the chocolate cools and solidifies, it contracts slightly and is released cleanly from the molds onto conveyors, ready for wrapping. Each chocolate piece is visually inspected, sometimes using high-speed cameras and vision systems, to ensure correct shape and fill. Hershey's Kisses, for example, go through dedicated foil wrapping machines that not only wrap each piece in branded foil, but also insert the iconic paper plume. Bars are fed into flow wrappers that apply sealed plastic or foil film, printed with lot numbers and expiration dates for traceability. From there, wrapped products are packed into cartons, sealed, labeled, and automatically palletized. Finished pallets are stored in climate-controlled warehouses maintained at stable temperatures and humidity to preserve texture, flavor, and appearance. Before any product is shipped out, samples from each production batch are tested in Hershey's quality control labs. There, technicians measure viscosity, particle size, pH, and fat content, and perform sensory evaluations to confirm that every batch meets the company's rigid standards for flavor and mouthfeel. Snickers, one of the most iconic candy bars in the world, is produced through a multi-stage industrial process that combines confectionery precision, mechanical engineering, and high-speed automation to create its distinctive layers of nougat, caramel, peanuts, and chocolate. Every bar must deliver the exact same ratio of texture and flavor, whether it's made in a facility in the United States, Europe, or Asia. With millions of bars produced daily, the manufacturing of Snickers is a tightly controlled operation with specific systems dedicated to each layer of the bar, all integrated into a seamless production line that ensures uniformity, food safety, and efficiency. From raw ingredient handling to final packaging, the Snickers factory operates with synchronized precision. Production begins with the preparation of the nougat layer, which forms the foundational base of every Snickers bar. The nougat used in Snickers is a whipped, chewy confection made from a combination of sugar, corn syrup, egg whites, milk powder, cocoa, and a small amount of salt. These ingredients are first loaded into industrial mixing vessels where they are cooked and then aerated. The sugar and corn syrup are heated together in a jacketed kettle until they reach a temperature between 115 degrees Celsius and 125 degrees Celsius. This heating process is tightly controlled through automated sensors that ensure consistent viscosity and prevent burning or crystallization. Once the syrup mixture reaches the desired temperature, it is transferred into a high-capacity continuous mixer, where egg whites and milk powder are added. Compressed air or nitrogen gas is also injected to whip the mixture into a soft, foamy texture. This aeration step is critical. It gives the nougat its characteristic lightness and chewiness. The temperature, gas pressure, and mixing speed are all precisely monitored by programmable logic controllers, which adjust the input in real time to maintain consistent product density and texture. The aerated nougat is then deposited as a thick slab onto a moving conveyor belt. This belt passes through a cooling tunnel that gradually reduces the temperature of the nougat slab to stabilize its structure. The cooling tunnel is divided into zones, each maintained at a different temperature to prevent rapid contraction, which could cause cracking or uneven density. Once cooled, the nougat slab is cut longitudinally into ribbons, the exact width of a Snickers bar, and then cross-cut into bar-sized sections using high-speed guillotine knives. These knives are synchronized with the conveyor's motion to ensure clean, accurate cuts without deforming the soft nougat. Next comes the caramel layer. The caramel used in Snickers is thick and elastic, designed to stretch but not melt under room temperature. It is made from a cooked blend of glucose syrup, sugar, milk solids, butterfat, and a carefully calibrated emulsifier. The cooking process begins in a steam-jacketed cooker, where the ingredients are brought up to approximately 118 degrees Celsius. The precise cooking temperature ensures the right balance between chewiness and flow. Overcooked caramel would become brittle, while undercooked caramel could seep through the nougat or ooze during packaging. Once cooked, the caramel is pumped into a depositor system that lays a continuous sheet of caramel over the cooled nougat ribbons. This depositor uses pressurized nozzles that spread the caramel evenly across the top surface of the nougat. The caramel is still warm and pliable at this point, allowing it to form a tight bond with the underlying layer. As the conveyor continues to move, the nougat and caramel combination enters another cooling tunnel where the caramel layer is firmed to a stable consistency. Here again, the temperature gradient is critical. The cooling must be fast enough to stop flow, but slow enough to avoid separating from the nougat base. After the caramel is stabilized, whole roasted peanuts are applied. Snickers uses high-grade peanuts that are dry roasted on-site or sourced from dedicated peanut processors. These peanuts are first cleaned, sorted, and passed through color and size grading machines. Roasting is carried out in rotary drum roasters, where temperatures are maintained around 160 degrees Celsius. After roasting, peanuts are cooled rapidly using ambient or forced chilled air to stop the cooking process and retain crunch. The cooled peanuts are then sprinkled over the still sticky caramel layer using a controlled vibratory feeder. These feeders dispense peanuts in an even distribution, and excess nuts are collected and recirculated to avoid waste. Once applied, the peanut caramel nougat stack moves through a compression station where soft rollers press the peanuts gently into the caramel to ensure adhesion. This step is essential to prevent peanuts from falling off during enrobing and packaging. The multi-layer slab is then cut again, first lengthwise into individual bar width strips, then crosswise into single units. High-speed ultrasonic knives are often used in this phase to make clean cuts through the sticky peanut caramel mass without dragging or deforming the shape of the bar. These knives vibrate at ultrasonic frequencies, reducing friction and keeping each cut smooth and precise. As with earlier cutting stages, sensors track bar dimensions, and any piece that falls outside specified tolerances is rejected automatically. Now, the cut bars are conveyed into the enrobing chamber, where they are coated with milk chocolate. The chocolate used in Snickers is a proprietary milk chocolate blend containing cocoa solids, cocoa butter, sugar, milk powder, and emulsifiers. This chocolate is kept in tempering tanks where it is heated and cooled in a controlled cycle to form stable cocoa butter crystals. Proper tempering is crucial for ensuring that the chocolate coating is glossy, has the right snap, and doesn't develop fat bloom over time. Inside the enrober, each bar passes over a fine mesh conveyor that dips the underside of the bar in chocolate. A curtain of tempered chocolate then flows over the top of each bar, fully enrobing it. Excess chocolate is removed by controlled air jets or vibrating mechanisms, which ensure a consistent coating thickness without pooling or streaking. As the chocolate sets, decorative ribbons or textures may be applied to the top surface using nozzles or air patterns. After enrobing, the bars enter the final cooling tunnel. This tunnel is typically 20 to 30 meters long and divided into multiple zones, with temperatures gradually decreasing from around 15 degrees Celsius to 5 degrees Celsius. The goal here is to allow the chocolate to crystallize into a firm, uniform shell without cracks or surface defects. Conveyor speed and cooling tunnel temperature are constantly adjusted to account for changes in factory humidity or chocolate flow rate. Once the bars exit the cooling tunnel, they move to the packaging area. Here, vision systems inspect the bars for defects, such as incomplete coating, misshapen forms, or incorrect size, and reject any units that don't meet quality standards. Accepted bars move into a high-speed flow wrapping machine. This machine dispenses printed plastic film from large rolls, forms it into a sleeve around each bar, seals the ends and back, and prints lot numbers, expiration dates, and traceability codes onto the packaging. Bars are grouped and packed into cartons automatically, then palletized using robotic arms or automatic stackers. Each pallet is labeled with its production date, factory ID, and batch number, and stored in a temperature-controlled warehouse. Finished Snickers bars are shipped daily to retailers, wholesalers, and export hubs with real-time tracking through the company's logistics and ERP systems. This ensures traceability from raw ingredient to retail shelf and allows for rapid recall or investigation if any quality issue arises in the field. Snickers production is supported by continuous quality assurance throughout every phase. From incoming raw ingredients to the final product, quality technicians perform random sampling and laboratory testing for moisture content, peanut roast quality, chocolate temper index, caramel viscosity, and microbial counts. Every component, nougat, caramel, chocolate, peanuts, is monitored to within narrow tolerances. If even a single component batch shows deviation, it can be traced, flagged, and excluded from the production cycle. In addition to quality, food safety and hygiene are rigorously maintained. All machinery is subject to clean-in-place protocols, and workers adhere to strict sanitation and allergen handling rules. Due to the presence of peanuts, dedicated production zones and air handling systems are used to prevent cross-contamination with other product lines in multi-product factories. The Snickers production process is also increasingly supported by digital technology. Smart sensors, machine learning models, and real-time analytics are used to monitor equipment performance, detect subtle variances, and suggest preventative maintenance. Digital twins of the production line can simulate different production scenarios, like ingredient substitutions or temperature fluctuations, to predict impacts before they occur in the real world. This data-driven approach allows Mars, Inc., the manufacturer of Snickers, to continuously refine and optimize its production across multiple global sites. Twix is a beloved chocolate bar recognized globally for its iconic combination of crisp biscuit, chewy caramel, and smooth milk chocolate. Its appeal lies in the precise layering and the uniformity with which each bar delivers the same balance of texture and flavor. Behind its simple appearance is a highly engineered manufacturing process that seamlessly integrates baking, confectionery science, and automated packaging on a vast industrial scale. Producing millions of Twix bars daily in factories around the world requires meticulous coordination across every step of production, from dough mixing to chocolate enrobing, all operating under strict food safety protocols and quality control systems. The following in-depth look walks through the entire process, detailing how Twix is made in a modern factory environment, step by step, with over 1,600 words devoted to the subject. The process begins with the foundation of the Twix bar, the biscuit base. This shortbread-like component is central to the signature texture of Twix, light, crunchy, and buttery without being too sweet. The ingredients for the biscuit base include wheat flour, vegetable oil or shortening, sugar, salt, and leavening agents. These raw materials are delivered to the facility in bulk, typically stored in stainless steel silos or sealed containers to protect against moisture and contamination. The dry ingredients are conveyed into high-capacity horizontal mixers, where they are combined with fats and a small amount of water. These mixers are programmed to replicate the specific time, temperature, and mixing intensity needed to create the ideal dough consistency. Overmixing is carefully avoided to prevent gluten development, which would make the biscuit tough rather than tender and crisp. The dough is monitored for temperature, moisture content, and texture using inline sensors, ensuring consistency across every batch. Once mixed, the dough is transferred to a sheeting machine. This equipment rolls the dough into a uniform sheet of precise thickness, typically between 5 to 7 millimeters, depending on the specific product variant. The sheet passes through multiple sets of rollers to ensure evenness, then moves toward a rotary cutter that stamps out the biscuit fingers. Each finger is carefully spaced on a baking band to prevent sticking or deformation during baking. Excess dough, or webbing, is collected automatically, recycled, and fed back into the mixer for reuse, minimizing waste. The cut biscuits are conveyed into a tunnel oven, often more than 30 meters long, and divided into multiple temperature zones. The ovens are typically gas-fired and utilize forced convection to ensure even heat distribution. Baking profiles are carefully managed. The temperature starts lower to allow for expansion and rises toward the middle and end of the tunnel to set structure and achieve the golden brown exterior. The baking process typically lasts around 8 to 12 minutes. The final product emerges dry, crisp, and structurally sound to support the next layers of caramel and chocolate. After baking, the biscuits are cooled on a long spiral or tiered cooling conveyor. It is essential that they reach ambient temperature before caramel application, as residual heat could soften the caramel or cause bonding inconsistencies. Airflow systems within the cooling unit are calibrated to prevent moisture buildup, which could compromise the crispness of the biscuit layer. Next is the caramel layer, one of the most technically challenging aspects of the Twix manufacturing process. The caramel must be viscous enough to form a thick, even layer on the biscuit, yet firm enough to retain its shape during cutting, enrobing, and packaging. It must also stretch slightly when bitten into, without melting or breaking apart. The caramel is prepared in large, jacketed cooking kettles or continuous caramel cookers. The ingredients, glucose syrup, sugar, milk solids, fats, and sometimes salt and flavorings, are heated to a controlled temperature around 118 to 120 degrees Celsius. Cooking caramel to the correct temperature is critical. Any deviation can result in too hard or too runny caramel. The factory's automated control systems monitor bricks levels, temperature curves, and viscosity in real time. Adjustments are made instantly if readings deviate from the set parameters. Once cooked, the caramel is pumped into a depositor system. This system deposits a continuous ribbon of hot caramel directly onto the cooled biscuit fingers, which are now moving along a precision conveyor belt. Depositors can be adjusted to control caramel height and width, ensuring even coverage. The caramel must adhere firmly to the biscuit and cool rapidly to a semi-firm consistency to hold its shape through the subsequent chocolate enrobing process. The bars now enter a cooling tunnel for caramel setup. This tunnel is maintained at a lower ambient temperature and spans several meters to allow gradual cooling without thermal shock. As the caramel cools, it solidifies just enough to support chocolate coating without running or shifting. This balance is critical for appearance, structural integrity, and mouthfeel. Once the biscuit and caramel layers are firmly bonded, the bars proceed to the chocolate enrobing phase. This is where each Twix bar is fully coated in a layer of milk chocolate. The chocolate used is a proprietary blend formulated specifically for Mars, Inc. And it includes cocoa butter, milk powder, cocoa solids, sugar, and emulsifiers, such as soy lecithin, to ensure proper flow. The chocolate is first tempered, a process that involves heating, cooling, and reheating to encourage the formation of stable cocoa butter crystals. Proper tempering gives the final chocolate coating its shine, snap, and resistance to fat bloom. In large-scale operations, tempering is achieved using continuous tempering machines that monitor crystal formation, viscosity, and flow rate. The tempered chocolate is pumped into an enrober, which is essentially a tunnel where a curtain of chocolate flows from above and a shallow pool coats the bottom. The bars pass through this curtain and are submerged briefly in the bottom coating layer, ensuring all sides are covered. Air knives or vibrating plates remove excess chocolate, and decorative features, such as surface ripples, may be added by adjustable nozzle heads or vibration patterns. The chocolate-coated bars are immediately conveyed into another cooling tunnel, this one much longer and colder, designed to gradually bring the chocolate to a solid state without creating bloom or surface imperfections. The cooling tunnel maintains a strict temperature gradient, starting around 18 degrees Celsius and lowering to 10 degrees Celsius by the end, over a 5 to 10 minute period. As the bars exit the cooling tunnel, they are fully formed Twix bars, but they're not yet individually packaged. They move directly into the high-speed wrapping area. Each bar is aligned and spaced using puck systems or lane guides to ensure it enters the flow wrapping machine correctly. Here, rolls of branded film are fed into the wrapper, folded tightly around the bar, and sealed on all sides using heat and pressure. The film is pre-printed with logos, batch codes, nutritional data, and sometimes promotional graphics. Each wrapped bar is weighed and passed through metal detectors or X-ray scanners to ensure it meets food safety standards. Any bar outside of weight tolerance or showing contamination is automatically diverted. Accepted bars are grouped into multi-packs or display boxes using robotic pickers or diverters, then loaded into shipping cartons. The cartons are coded with tracking data and palletized using automatic palletizers. Each pallet is scanned into inventory and staged for shipping. Throughout the factory, quality control technicians pull samples at regular intervals to test for key performance attributes: biscuit density, caramel thickness, chocolate adhesion, weight, sensory characteristics, and packaging integrity. The factory also operates under a HACCP framework, meaning each step of the process is mapped for potential hazards and monitored with critical control points. Twix manufacturing is highly dependent on repeatability, and thus, much of the factory's infrastructure is built around statistical process control and automation. PLCs communicate with sensors on every machine, feeding data to a centralized control room. This enables supervisors to watch live readouts of oven temperatures, caramel cooker output, chocolate temper readings, fill weights, and wrapper speed, all updated every second. Alarms and automatic corrections are built into the system, allowing for real-time adjustments without stopping production. Beyond process precision, Twix production lines are designed for flexibility. Factories can run product variations including Twix miniatures, Twix ice cream bars, Twix cookies and cream, or seasonal additions like white chocolate or dark chocolate. Changeovers between product formats involve switching molds, adjusting depositor nozzles, changing film rolls, and flushing chocolate lines, all of which are guided by detailed standard operating procedures to avoid cross-contamination and ensure food safety. Once finished, Twix bars are shipped to distribution centers or directly to retailers. During shipping, temperature control remains important, particularly in warm climates where chocolate is susceptible to melting. Pallets may be moved using temperature-controlled trucks or packed with insulation to protect product integrity. Inventory is rotated on a first-in, first-out basis to ensure freshness and shelf life management. At the retail end, Twix must retain not only its visual appeal, but its textural signature. The snap of the biscuit, the chew of the caramel, and the smoothness of the chocolate are all the result of hundreds of synchronized steps and checks across a production system built for consistency at scale. From ingredient sourcing to the final shipping pallet, every detail is fine-tuned to preserve the brand's identity and ensure that each bite of Twix tastes exactly as expected: crisp, creamy, and perfectly layered. To craft Starburst, factories begin with a foundation of raw materials, with the primary ingredients being sugar, corn syrup, hydrogenated palm kernel oil, fruit juice concentrates, citric acid, and natural and artificial flavors. Food-grade colorants such as red 40, yellow 5, and blue 1 give the candy its vibrant, recognizable hues. Sugar, the dominant ingredient, is typically sourced from sugar beets or sugar cane, refined to a fine, white granulated form. Corn syrup, essential for achieving the chewy consistency, is extracted from dent corn and then enzymatically converted into glucose-heavy syrup. This syrup not only sweetens, but also inhibits crystallization, allowing for the distinctive, flexible Starburst chew. Fruit juice concentrates are selected based on seasonal availability and flavor profiles, often involving apple, cherry, orange, strawberry, lemon, and other citrus bases. Each concentrate is filtered and reduced under vacuum conditions to intensify the flavor while removing excess water. Meanwhile, citric acid, either derived from citrus fruits or biosynthesized using Aspergillus niger fermentation, is added to sharpen the tart notes and stabilize the pH level. Palm kernel oil, after undergoing hydrogenation to solidify its structure, contributes to the smooth mouthfeel, acting as a lubricant and textural agent within the candy matrix. All of these ingredients are delivered to the factory in bulk. Sugar and corn syrup via silo systems and tanker trucks, oils in heated storage tanks, and flavoring agents in sealed food-grade containers to maintain freshness and prevent contamination. Once inside the facility, the first major step in the Starburst making process is ingredient weighing and batching. Massive computerized batching systems measure exact quantities of each component using load cells and automated valve controls. Sugar and corn syrup are combined in stainless steel jacketed mixing tanks where they are preheated to around 115 degrees Celsius. This begins the process of dissolving the sugar crystals into a homogeneous syrup base. Agitators inside the tanks ensure uniformity and prevent scorching. The heated syrup is then transferred to a vacuum cooker. In the vacuum cooking chamber, the syrup is exposed to reduced atmospheric pressure, allowing water to evaporate at a lower temperature. This technique is critical in candy making, as it prevents the sugar from caramelizing or breaking down under intense heat. As moisture is removed, the syrup thickens into a viscous mass with a specific Brix value, typically between 85 and 90% solids content, ensuring it will solidify into a chewy form once cooled. The exact cooking time and temperature are closely monitored via sensors and control systems linked to the plant's supervisory control and data acquisition platform, or SCADA. After cooking, the thickened candy mass is transferred through heated conduits into a mixing chamber known as a color and flavor cooker, or kneader. Here, hydrogenated palm kernel oil is added to help emulsify the mixture and control the final texture. Food-safe mixing blades, often paddle style or Z-blade types, churn the mass at controlled speeds. This is also the point where colorants, acids, and flavor concentrates are injected. High-precision peristaltic pumps ensure accurate dosing of color and flavor to maintain batch consistency, and the mixer is divided into multiple compartments if producing more than one flavor at a time. For instance, strawberry might be mixed in one chamber, lemon in another, and cherry in a third. Each batch customized with different concentrations of fruit essence and specific pH levels for optimal taste balance. Once the flavor-specific masses are ready, they must be cooled to a workable temperature, typically around 60 degrees Celsius, before shaping. Cooling belts equipped with air curtains and stainless steel rollers gently lower the temperature without causing hardening or premature setting. From here, the candy mass is directed into the forming line, a highly orchestrated system of extrusion, cutting, and wrapping. Extrusion is the next key phase. Using positive displacement gear pumps, or auger-driven extruders, the warm candy mass is pushed through stainless steel nozzles with rectangular cross-sections. This creates long, continuous ropes of candy with a consistent width and height, matching the final Starburst dimensions. Servo motors carefully control the extrusion speed to synchronize with the downstream cutting process. If multiple colors or flavors are being co-extruded, special twin-screw extruders equipped with internal baffles can combine two masses into a single dual-colored strand. which adds visual interest and flavor complexity. The ropes move onto a conveyor equipped with cooled rollers to maintain their shape. A high-speed guillotine cutter, controlled by an optical sensor system, slices the rope into individual blocks with precise timing. The cutting knives are made from food-grade stainless steel and are lubricated with a microfine spray of food-grade oil to prevent sticking. Each candy piece is now in its iconic rectangular shape, ready for wrapping. Wrapping Starburst is a marvel of mechanical ingenuity. Each piece must be individually wrapped in waxed paper to preserve freshness and prevent sticking. Automatic folding and wrapping machines, operating at speeds of up to 800 pieces per minute, perform this delicate operation with stunning precision. These machines use synchronized mechanical arms to position each candy, fold the wax paper around it using rotary folding drums, and seal it using gentle pressure rather than heat, which might soften the product. The wrapped pieces are then collated by vibratory feeders and assembled into 4-piece packs in various flavor assortments. These grouped candies are fed into a horizontal flow wrapper, where they are encased in the familiar branded packaging film. The flow wrapper uses a combination of rollers, film unwinders, photo eye sensors for alignment, and end-sealed jaws to create hermetically sealed packages that protect the candy from moisture and oxygen. The film is often reverse printed with branding, nutritional information, and batch tracking codes. Nitrogen flushing may be used in some production lines to displace oxygen and extend shelf life. After packaging, each unit passes through metal detectors and X-ray scanners to ensure there are no foreign objects or contaminants. Vision inspection systems verify print clarity, package seal integrity, and correct product count. Random samples are pooled for manual inspection by quality control technicians who assess texture, flavor, intensity, size, and appearance. Finished goods are then loaded into cartons by robotic case packers and labeled with lot codes for traceability. These cartons are palletized by robotic arms equipped with vacuum grippers, stacked in strategic configurations to optimize warehouse space and prevent crushing during transport. Once pallets are complete, they are shrink-wrapped and transferred via automated guided vehicles to temperature-controlled storage areas. Though Starburst is shelf-stable, storing it in a cool, dry environment prevents oil separation, flavor degradation, and textural hardening. From these warehouses, Starburst products are shipped out via freight trucks or distribution centers, eventually reaching retail shelves in supermarkets, vending machines, and convenience stores around the world. What makes the Starburst manufacturing process particularly interesting is the interplay between artistry and automation. While the ingredients themselves are simple, achieving the exact chewiness, vibrant color, and flavor burst that consumers expect requires precision-engineered machinery, tight process control, and an unyielding commitment to consistency. The smallest variation in moisture content, mixing speed, or cutting pressure could result in a piece that's too hard, too sticky, or aesthetically flawed. Despite being a candy rooted in simplicity, the industrial complexity behind Starburst underscores the broader evolution of confectionery manufacturing. Today's production lines incorporate real-time analytics, inline spectroscopy for flavor consistency, and even machine learning algorithms that predict equipment maintenance needs to avoid downtime. Some newer factories are experimenting with plant-based colorants and sustainable packaging materials, aiming to meet consumer demand without compromising on quality. There's even ongoing research into using recycled steam and closed-loop water systems to reduce the environmental footprint of candy production lines like those making Starburst. Mentos were first created in the early 20th century and gained global popularity due to their unique texture and intense flavor. The combination of a crunchy outer coating and a chewy interior is what sets them apart, and achieving that contrast requires precise formulation and processing. The base recipe revolves around sugar, glucose syrup, hydrogenated coconut or palm kernel oil, gelling agents like gelatin or modified starches, natural and artificial flavors, food-grade colorants, and glazing agents such as carnauba wax. Depending on the variety, mint, fruit, cola, or sour, the flavoring system will differ, but the core production mechanics remain largely the same. Production begins with the sourcing and handling of raw ingredients. Sugar is delivered in bulk form, typically refined cane or beet sugar, and stored in large silos within the factory. Glucose syrup, derived from enzymatically treated cornstarch, arrives in insulated tanker trucks and is stored in jacketed holding tanks to keep it fluid and at the proper viscosity. Oils are stored in temperature-controlled containers to maintain consistency. Each of these raw materials is subjected to a series of pre-checks. Sugar is tested for grain size and moisture content, glucose syrup for dextrose equivalent values, and oils for peroxide levels and stability. The factory's quality control department samples all incoming ingredients and verifies their compliance with specifications using chromatography, spectroscopy, and other chemical assays. Once approved, the first step in making Mentos centers on the formation of the candy core. Unlike many confectionery items, the chewy center of a Mentos is not extruded or cast, but formed using a process called compression or tableting. But before compression can occur, a slurry is created by blending sugar, glucose syrup, and oils in large mixing kettles equipped with paddle agitators. This mixture is partially cooked to evaporate water and develop the candy's elasticity. Once it reaches the desired consistency, typically with a Brix reading of about 85% solids, it is transferred to a cooling table where it is kneaded to achieve the ideal texture. The cooled mass is then broken into chunks and fed into a granulator, which reduces it into fine, uniform particles suitable for compression. These particles are sieved to ensure consistent particle size, which is critical for proper tablet formation. A binding agent, often modified starch or gelatin powder, is then added to help the particles fuse during compression. The powdered base is then fed into rotary tablet presses, high-speed machines equipped with stainless steel dies and punches that compress the powder into uniform cylinders. Each tablet is subjected to high compression force to achieve the dense, elastic core that is characteristic of Mentos. These presses can produce thousands of tablets per minute, and they feature real-time monitoring systems to ensure weight, hardness, and thickness are within specifications. The freshly compressed tablets are soft and not yet glossy. At this stage, they are known as centers and will undergo further processing to become the finished product. These centers are now ready for the panning stage, a method of coating used to apply multiple layers of sugar and flavor to build up the candy shell. The panning process takes place in large, rotating stainless steel drums called coating pans or Drageses pans. The cores are loaded into the pan, which rotates at a controlled speed while fine sprays of syrup, flavor, and color are applied in successive passes. Initially, a syrup consisting of dissolved sugar and glucose is sprayed onto the tablets using atomizing nozzles. Hot, dry air is simultaneously blown into the pan via air ducts, which rapidly evaporates moisture and causes the sugar to crystallize onto the surface of the tablets. This process is repeated over and over, sometimes more than 30 times per batch, to gradually build up the characteristic crunchy coating of Mentos. During these cycles, food-grade colorants and additional flavoring agents are also introduced. Different panning cycles are used for mint and fruit flavors. For example, mint Mentos typically receive a higher concentration of menthol and peppermint oil in the outer layers, while fruit Mentos require individualized flavor additions like strawberry, orange, and lemon each blended with acidulants such as citric or malic acid to amplify the taste. Achieving uniform coating thickness, color distribution, and surface smoothness requires expert control of several variables: syrup viscosity, pan speed, airflow rate, and ambient humidity. Most modern Mentos facilities use programmable logic controllers and environmental monitoring systems to automate these parameters and ensure repeatability across batches. The entire panning process can take several hours, as each layer must dry before the next is applied. Operators use inline sensors and visual inspections to check for surface integrity, ensuring that no rough spots or cracks appear as the coating thickens. Once the desired shell thickness is achieved, the tablets undergo a drying and stabilization phase in climate-controlled holding rooms. Here, they rest for several hours, allowing residual moisture to equalize and the structure to firm up. The next step is polishing, a critical final touch that gives Mentos their trademark shine and smooth finish. Tablets are reloaded into specialized polishing pans and treated with a mixture of glazing agents such as carnauba wax and microcrystalline wax dissolved in ethanol or isopropyl alcohol. As the pan rotates, the wax mixture is sprayed lightly onto the surface of the tablets and then buffed by friction as the candies tumble against one another. This step not only enhances visual appeal, but also serves a functional role, creating a moisture-resistant barrier that extends shelf life. After polishing, the finished candies are cooled again to harden the glaze and prevent sticking. They are then conveyed to the packaging area via vibratory conveyors and sorting belts that align them into consistent orientations for loading. Modern Mentos factories use high-speed flow wrapping machines capable of packaging dozens of rolls per minute. The individual candies are fed into paper or plastic film wrappers, which are then heat sealed and crimped into the familiar cylindrical Mentos roll. These rolls are typically grouped into multi-packs or display trays using robotic case packers and then passed through labeling stations where batch codes and expiration dates are applied using inkjet or laser printing systems. To ensure food safety and quality, each roll passes through a series of automated inspection stations. X-ray machines and metal detectors scan for foreign objects, while vision systems inspect label placement, roll integrity, and seal quality. Statistical quality control sampling is performed by trained technicians who manually test rolls for chewiness, coating hardness, gloss level, and flavor profile using a standardized scoring system. Any deviations trigger a hold on the batch and a review of equipment calibration and ingredient records to pinpoint the source of variation. Pallets of Mentos rolls are finally shrink-wrapped and transferred to the factory's finished goods warehouse, where they are stored under tightly controlled temperature and humidity conditions. Though Mentos are relatively shelf-stable, proper storage conditions ensure they retain optimal flavor, texture, and appearance for months. From there, the products are distributed through regional logistics hubs to retail outlets around the globe. While consumers might simply pop a Mentos into their mouth without much thought, the reality is that each piece embodies a tremendous amount of behind-the-scenes engineering. From the uniform density of the core to the microscopic layering of sugar shell, every step in the process is fine-tuned to ensure consistency at massive production scales. Advanced data analytics platforms are increasingly being used in Mentos factories to track machine performance, ingredient variation, and environmental fluctuations, helping operators predict and prevent quality issues before they occur. The candy's production is also seeing innovations aimed at sustainability, including the use of biodegradable wrappers, energy-efficient panning systems, and closed-loop water recycling technologies. Some manufacturers are exploring plant-based gelling agents to create vegan-friendly versions of the product, expanding the Mentos appeal to a broader market while keeping the signature experience intact. The story of Skittles production begins with the sourcing of raw ingredients. The core of each Skittle consists primarily of sugar, corn syrup, and hydrogenated palm kernel oil, combined with fruit juice concentrate, citric acid, natural and artificial flavors, and gelatin or a plant-based gelling agent, depending on the variety. Food colorants such as Red 40, Yellow 5, Blue 1, and others provide the vivid, rainbow-like appearance, while carnauba wax is used for the final shine. All ingredients arrive at the factory in bulk, sugar in pneumatic tankers or super sacks, corn syrup in heated tank trucks, oils in insulated totes, and flavors and colors in sealed drums to preserve potency and prevent contamination. Once the raw materials are delivered to the facility, they undergo quality inspection. Sugar is tested for purity and grain size using optical sensors and moisture analyzers, while corn syrup is evaluated for its dextrose equivalent to ensure consistent sweetness and viscosity. The oils are checked for oxidative stability and melting point, and flavor compounds are tested with chromatography to confirm identity and strength. Approved ingredients are then routed to ingredient storage silos or intermediate tanks, each connected via stainless steel piping to the central mixing systems. The production of Skittles begins with the creation of the chewy center, which is not molded or extruded like many other candies, but rather formed through a process known as casting or deposition. First, sugar, corn syrup, and oils are combined in large, stainless steel, steam-jacketed kettles. Agitators mix the contents while the batch is heated to around 115 to 120 degrees Celsius. This heating step is critical. It dissolves the sugar, reduces viscosity, and activates the gelling agents that will give the Skittle its characteristic chewy texture. Once the mixture reaches the desired consistency, it is partially vacuum cooked to remove excess moisture, yielding a thick, elastic syrup. This candy mass is then deposited into starch molds, which are preformed trays filled with cornstarch that contains indentations for each candy. Depositing heads, essentially nozzles controlled by servo-driven pumps, release precisely metered amounts of the syrup into each cavity. These molds are then transferred via conveyor into a climate-controlled drying tunnel where they remain for 24 to 48 hours. During this time, water evaporates slowly and uniformly, and the chewy texture begins to set. After drying, the starch is separated from the candy cores using a destarching system. This equipment gently shakes and brushes off the remaining starch, which is collected, filtered, and reused in future cycles. The now formed Skittle centers are tumbled in large rotating drums to smooth their surface before being passed to the next critical step, the sugar shell coating, also known as panning. Panning is a cornerstone of Skittles production and one of the most technically demanding phases of the process. The centers are placed into enormous rotating pans, typically several meters in diameter, where the sugar coating is built up through dozens of thin layers. Each pan spins continuously, and while it does, a fine sugar solution is sprayed onto the candy centers. This syrup typically consists of refined sugar, glucose, water, and sometimes citric acid for tartness. Immediately after spraying, a blast of temperature and humidity-controlled air is directed into the pan, drying the surface and forming a thin, hard layer. This coating process is repeated many times, sometimes for several hours, depending on the desired shell thickness. Different flavor syrups are added at different stages if multiple fruit profiles are being used within the batch. The rotation speed, spray volume, airflow rate, and drying temperature are all managed by PLC-controlled systems that monitor pan performance in real time, ensuring consistency in shell formation. Operators oversee the process via touchscreen HMIs, adjusting parameters based on real-time data and sensory feedback from test samples. Once the shell has reached its final thickness, color is added. This is typically done with 1 or 2 additional layers of tinted sugar solution, each one custom formulated for a specific flavor variant. Red for strawberry, yellow for lemon, green for lime or apple, purple for grape, and orange for naturally orange. These solutions include FDA-approved food dyes stabilized with acidulants and emulsifiers to ensure even distribution and adhesion to the candy surface. The result is a batch of candies, each uniformly colored, with a bright and durable outer shell. Next comes the finishing stage, where Skittles are given their unmistakable gloss. This is achieved using polishing pans and a mixture of carnauba wax and microcrystalline wax, sometimes diluted in alcohol to aid dispersion. The candies are tumbled gently while a fine mist of the wax solution is sprayed onto them. As the pan rotates, the candies polish each other through friction, creating a smooth, shiny finish. This step also provides a moisture barrier that helps extend shelf life and prevents the candies from sticking together in the package. After polishing, the Skittles are passed through cooling tunnels to solidify the coating and stabilize the structure. Then comes the critical stage of flavor sorting and portioning. High-speed sorting machines equipped with optical sensors separate the candies by color, using burst air jets to redirect them into designated channels. This ensures that each bag or pack of Skittles contains the full assortment of flavors in consistent proportions. The sorted Skittles are then conveyed to packaging stations, where they are portioned using volumetric or weight-based fillers. Each batch is dispensed into the appropriate packaging format, whether single-serve pouches, resealable share bags, or rigid tubes. The packaging film is reverse printed with branding, nutritional information, and traceability codes, and it is fed into horizontal or vertical form-fill seal machines. These machines form the pouches, fill them with product, and seal them in one continuous motion. Precise temperature and pressure controls ensure that the seals are airtight without melting the product inside. As the packaged Skittles exit the line, they are subjected to a series of inspection checkpoints. Metal detectors, X-ray systems, and vision scanners verify that each package contains the correct amount, is sealed properly, and is free of contamination. Random samples are pulled for quality testing, evaluating chewiness, shell thickness, flavor strength, and visual appearance. Some factories even use texture analyzers and sensory panels to verify that the candies meet brand specifications. Once approved, the packages are collated into cartons using robotic case packers and then palletized by automated stacking systems. Each pallet is stretch wrapped for stability and labeled with tracking information, including production time, line number, and batch code. Pallets are then routed to the warehouse, where they are stored in temperature and humidity controlled conditions to maintain optimal product integrity. Skittles are remarkably shelf stable, but proper storage conditions ensure that the texture remains soft and the colors do not fade. From the warehouse, Skittles are distributed via truck to retail distribution centers, grocery stores, vending machines, and online fulfillment facilities. The journey from raw ingredients to store shelves is timed to ensure freshness and consistency, with sophisticated supply chain software tracking every shipment to maintain inventory and respond to fluctuations in demand. The production of Skittles is not only an example of precision manufacturing, but also one of mass customization. Despite being produced in colossal quantities, every single piece must conform to strict standards of flavor, size, color, and texture. Innovations in data analytics, predictive maintenance, and machine learning are being introduced into Skittles factories to continuously improve yield, efficiency, and sustainability. Energy-efficient drying systems, water reclamation units, and biodegradable packaging research are helping the brand minimize its environmental impact without compromising the product's appeal.